Oh, it was muted. Okay, now? Yes. Perfect. So shall we get started? Great. So welcome everybody to the Ada DevRoom. It's been a couple of years since we've had not one of them. And we have quite a few updates in terms of projects, in terms of technologies related to the language, and also some introductory talks if you are new to the language and you would like to learn some of it. This DevRoom has been done in collaboration with Ada Europe and Ada Belgium. I will let the president of Ada Belgium introduce these two institutions a little bit in case you would like to know a little bit more.
Okay, thank you, Fer. So a few words about these organizations. These are all non-profit organizations that were set up with the main aim to promote the Ada programming language and technology. There are several of these in many countries, Belgium among others, also other countries as indicated there. And historically there was this Ada Europe organization, which was a kind of federation of all the national organizations. Over time this evolved to become an organization that has members worldwide, also direct members in countries where there is no national organization. And these non-profit organizations do various activities. The main ones are by Ada Europe, and that's threefold, the main activities. One is an annual conference in the International Conference on Reliable Software Technologies series. That's every year in another country. We try to go to several countries where there are teams that are, or people that are interested and willing to help with the organization. We also publish a journal, the Ada User Journal, 4 times a year, already for many, many years. This year is the 45th edition. And the third main activity is support of the language evolution and standardization under ISO that we try to support and maintain. I mentioned the conference. The previous one was in Barcelona in Spain. The next one is mid-June in Paris. Well, you see some pointers. There is a little flyer as well, which has links to all the important pages. For the conference, the call for papers is still open. For the journal track, it's very, very close, so that's a bit too late. But for all the other tracks, we still have, there's still an opportunity to submit. And there's a small flyer of 2 pages on the web page for this small opening talk, where you find more information. So I'd say enjoy the DevRoom and get your sticker if you want one to put on your laptop or somewhere else. Enjoy it. Okay.
So, now we will move on to the actual presentations. Once again, don't be shy and grab as many things as you want, and the flyers that Dirk has, please. We brought them here not to live with them back home. So, without further ado then, I will be working on the introduction to the updates in the Ada ecosystem in the past few years. So let me make sure I have both hands free. FOSDEM 2025 slides updates. There we go. And no. Aha. So, I think we are on time to get started, or maybe 1 minute. No, it's already 0.5. So, let's get started. So, since we didn't have a DevRoom in the past few years, a lot of people have probably thought of as Ada just kind of being there alone and not having many changes, but that's quite not true. And even within the Ada community, a lot of people don't know some of the new features that the language has gained in the past few years. So I wanted to update this a little bit. So what we are going to see today is the new Ada 2022 standard that came out a couple of years ago. A new Wish compiler that we have, which has added a couple of new cool features. Some Spark improvements, I will tell you what that is. Some tooling improvements and some Ada users, some users of the language, one of which hopefully will catch your attention quite a bit. So, Ada 22, new features. The language is not dead, it's still being developed. The new standard is being worked on already. Some features, we gained some functionally somewhat features with some iterator filters and a reduced attribute for arrays and for loops. We have declare expressions. One of the things people hate about Ada is the introduction of new variables. Ada is very strict where you can declare new variables and where you can put them. The declare expressions will hopefully aid that a little bit when you just need a quick variable to use in a quick expression. We also gained static expressions. So when you have a functional expression and you add the static attribute, it's compile time evaluatable. So we also gain some basic compile time evaluation, which will be worked on in future additions. Also, if you use the declare expression within a functional expression, you can create fairly complex functions that are compile time evaluatable. The image attribute, that's something people don't like about Ada, the way we print values to strings, the way we transform them. Well, now the compiler will automatically declare the image attribute for all data types, even composite data types, like structures, arrays, etc. And if you don't like the default one, there is the put image attribute for your types, so you can just tell it to use your custom printing procedure. Some basic quality of life improvements in Ada. Delta aggregates, very cool feature. When you have an object, an array, a complex data structure, and you just want to update several fields of it, instead of having to do several assignments, each with the different change you want to do, just use a delta attribute, the delta operator, and voila, you just say the small changes you want. This can be used to copy data from one attribute into a new one with just small changes. It's a huge life improvement. Index parameters for arrays, and also the assignment target name. You can now use the @ symbol to refer to the left-hand side. So in Ada, Ada is well known to have very long names, and people don't like to type them. So if you want to just use a short change to your data, you can use the @ symbol to do that. Also, that's the changes to the syntax. We have some changes to the libraries. We gain big integer support. We will get a big integer talk later, but it's a different implementation. It's for cryptography, constant time evaluation, whatever. The one in the standard library is up to the compiler to decide. We also gain atomic operations. We already had atomic data types in Ada, but we didn't have a package specific to deal with them. So now we have support for variadic functions. Ada is wonderful when it comes to interoperability with C, with Fortran, with COBOL, and can add also you can even interface with Pascal if you want. But one of the pain points were variadic functions, as Ada does not support them. Well, now there is a quality of life improvement if you have to deal with those in Ada. The non-blocking aspect, if you are into real-time operating systems, high-performance stuff like video games, very useful. The Jodovic profile, if you know what profiles are, great. If you don't worry about it. And first-class parallel support, we gain a new keyword, the parallel. It's meant to make parallel loops and iterators, etc., much faster. Just throw it around and let the compiler parallelize your code. It's still not supported in the compilers. All the other features are available in GCC, GNAT, and GNAT LLVM. Actually, there are more features that are already supported for the new standards that's going to come out. Some of them are really nice, but I didn't want to mention them today. I will let you read the change logs of the compilers that I usually write. Also, reminder, the Ada reference manual, the standard, is free for everybody, unlike SQL or C++ or C, where you have to pay hundreds of euros. This, in Ada, we try to make things open for everybody. So, that's all for the language. Let's go with Gnat LLVM, which, yes, one question?
So the at, is that textual replacement, or is that like everyday?
So the question was whether the at symbol is, I'm just doing this for the online people, whether it's a textual change of the data or a reference, etc. It's just it's textual replacement of the left-hand side of the assignment. Simple and easy.
So if, for example, the expression in your case had a side effect, ugly style, but whatever, then the side effect will be done several times.
Yes, so if it has side effects, it will happen. Though in Ada we hate those, so careful with that. But you can use the at symbol, for example, in function calls. So you have left-hand side, some function called at. So yes, it will have side effects. So Gnat LLVM, we have now a new compiler in town. It's not really new. It's the Gnat, the GCC frontend, bolted into the LLVM infrastructure. You may be asking yourself, so why do this? Well, LLVM has some features that are not available in GCC, mainly WebAssembly support and Morello, Sherry support, also some CUDA things that I will talk about later. And we have, some people of the community have already used the WebAssembly support to create web apps and just work with them. One of them is this little, I think I left it's not the interactive one. To print the slides I had to use a picture because I couldn't use the website. But you can go into the link I added you, GNAV, and this is a gliding navigation system. And it runs directly in your browser. The guy that did it is from here, from Brussels, and he runs his own glider in his Raspberry Pi in his Google Chrome browser. And it has like real-time information from like wind providers, some simulation support. It's pretty cool. Spark, for those of you who do not know Spark is the verifiable subset of Ada, although that's no longer quite true. Spark in the past few years has gained a lot of new features, and it's no longer that much of a subset of Ada. It's mostly all of Ada. So in 2019, we gained the borrow checker support, so Spark is fully memory safe. Previously, you couldn't do dynamic memory in Spark. It was forbidden. Now you can, using the borrow checker as it takes place in Rust. Actually, there is a slight improvement. Lifetimes are inferred because Spark is a full program analysis. So you don't have to annotate your things with Spark. Last year we gained exception support in Spark, which was another big mission feature from Ada. So now the creation, transmission, the handling of your exceptions throughout your entire program is provable. You can prove that you are doing things correctly. Some termination analysis improvements, that's really cool. Some people are like, can provers show termination of programs? Well, in some cases now they can do so automatically. And of course, some improvements to the provers, the underlying technology that does the proving for you, that they do the heavy lifting. Also, wonderful new library, SparkLib. SparkLib is basically a formally verified standard library, so you have maps, sets, everything. It's fully memory correct, it's fully runtime, what we call AORT, so absence of runtime errors. It's fully correct, you can formally use it, it's great. It has unbounded variants of the features, so if you want to do dynamic stuff, you can, big nums. And also a large part of the Ada standard library, that's something a lot of people don't know, in Gnat has been also formally verified. So if you do like you use the matrix package, everything is annotated to make sure that if you feed it correct data, you will get correct data. It will not handle incorrect data. You will get, as soon as possible, an error in the Spark, in the prover. Tools, Allir, a lot of people don't know it. It's the Ada's package manager. It's modeled after Rust's Cargo. Last year we had our version 2.0 release with the Allir install command, so now you can install your Ada programs at the system level. It has some quality of life improvements, some tool chains, some ARM, especially in the Mac section, some ARM improvements there. And we are trying to expand the ARM support in Alier because we are using GitHub runners for the free ones. Like a couple of weeks ago, they entered public beta, so we will try to get the toolchains built as soon as possible for you, and also Gnat LLVM. And as always, help is welcome to improve the packages there. Great news, in my humble opinion. Ada Core finally stopped their distribution of the compiler. That was causing a lot of issues within the community, a lot of confusion, because people thought, hey, that company is the one providing the compiler, and it's GPL only. What's happening? Wasn't this supposed to be like LGPL, like normal GCC stuff? And that was causing a lot of confusion, so they decided to stop doing that. And mostly because now, since we have Alier, if you wanted to use all the tools that they provide, they have been packaged there. So now you can just install them for your own project and go ahead with them. So, great. Also, it's not like they have stopped. A lot of the libraries they provided were GPL. They've changed their licenses to Apache. This is a bit of a philosophical thing, but a lot of people tend to prefer Apache for low-level libraries. So that's an improvement. And of course, they have kept on improving the Gnat Studio IDE for Ada, the Ada language server, which also supports VS Code in case you prefer to use it. And of course, the rest of the community has been updating their stuff. We have embedded systems, compilers, VHDL compilers, Vulkan bindings, etc. So feel free to just use whatever. In terms of community, a lot of you may not be aware, but there is a new community website that tries to modernize the Ada experience. That's Adalang. It has instructions how to quickly get started with Ada, how to set it up. It has tutorials. It has a huge forum that's quite active. I think a lot of us here are active there, so if you have questions or anything, please come and join and we'll try to help you. Also, the Ada User Society, it's trying to be a global institution. As Dirk presented the European side of things, some people felt left out, so we wanted to also have an institution that would provide them a home to be part of and take part in discussions of the Ada development. So if you have feedback for Ada, the Ada repertoire group, which is hosted, it's kind of close to the Ada User Society, you can go into their GitHub and propose new changes to the language, and they will discuss them with you, and if they like them, they will propose them for you. So we are trying to also get the Ada standard a little bit more of a community feedback. Also, last year, NSA recommended Ada as a memory-safe programming language, which is a bit of a surprise because Ada is not memory-safe. Ada Spark is. However, it kind of makes sense they did. Ada was developed by design to be safe in a lot of areas, not just memory safe. And the language design and the features it has help you get everything correct. It has control types, limited types. These features tend to be quite advanced, and people tend to forget that they exist, but they are in the language. And the compiler, just by design, the type system, etc., dynamic, implicit dynamic and allocation, and the allocation will get you quite far. Also, memory pools. A lot of people don't know we have them. They are known as memory arenas in a lot of languages. We have those. Custom allocators, by default, like everything is in the language. But of course, if you need 100% memory safety, just go ahead and use Spark. Also, you will get runtime safety, exceptional safety, everything safety, so not just memory. How many of you knew that NVIDIA was using Ada Spark? If you are using a new NVIDIA graphics card, you are probably running a Spark. Since 2019, they decided to go with Ada Spark because they need to get their hardware and their software certified for safety critical applications like self-driving cars. And they did an assessment on what languages they should use. They looked at C because it had some verified toolchains. They looked at Rust too. And they decided that Spark was going to be Ada Spark was going to be their thing. They liked it so much that they even contracted Ada Core to develop a CUDA binding so that you can program CUDA directly from Ada. But it's not fully open. The library is. You can go ahead. It's in GitHub. You can take a look at it. There are tutorials on how to use it, but the toolchain is not really that open. And we know they liked it. Why? Because NVIDIA has a white hat hacker team inside their company, and they try to break their own software. And they went to DEF CON to tell their stories and how it went to their adventures when trying to break Ada. Their first DEF CON 29, they gave up and they broke the RISC-V ISA instead. It was easier. So hardware was the weakest link. On DEF CON 30, they probably got up much better, and they started finding some issues in the Ada core. And they compared them to safety critical C code that they had and the Spark code. You can watch the videos, so you didn't have to trust me, but they found that the quality was much better. Also, a lot of the information they give about Spark has become outdated. That's why I updated you a little bit on that. Although everything looks good, there are some challenges ahead. I think we as a community need to improve the tools quite a lot. The experience, learning experience, the tutorials, etc. It needs to be heavily improved compared to other languages, but we are working on that. Also, if you would like to learn Ada, there is Learn Ada Core. You don't even have to install the compiler. It has interactive compilation boxes where you can type Ada and solve the exercises and see how things break or not. It has some courses. They added some intermediate courses, learning things. And if you're coming from Embedded C, they have a specific course for you. Misra C, C++, Java. If you have any of those backgrounds, go ahead and look at the specific sections, because you will have a much better experience with them as they target your previous experience. So that's everything from me. Thank you for your attention. I'm open to questions here now, or my inbox is more than open, and hopefully we'll see some of you take on the Ada language. So thank you. So we have some time for questions. If you have them, feel free to ask them. If not, we can get it started with the next talk, which will be how to get it started with Ada in like 2 minutes, 5 minutes.
You should never start early.
No, I know we want to start early. But in case you didn't know, the experience, especially on how to get it started, has become a lot easier thanks to some packages that, thanks to Alir, thanks to some packages that have been created. So I encourage you to take on the Ada. If you have issues with the language, come to the community. We are here to help. Also, a bit of an issue that the Ada community has. We tend to just tell new people, oh, here's the standard, go and read it. And people don't like that, especially new people, because they are not used to it. Fun fact, the Ada standard has been written in such a way that anybody can read it, not just compiler developers. So don't be afraid to use it, don't be afraid to open it and go into the different sections and discover what the language has to offer. And it has a lot of small details that most people don't know, and that's something I'm trying to improve. Some people don't know we have control types, finalizable types, that's coming this year, limited types, and most people don't have these features in other languages, so they don't know they exist in Ada. So we are working on that to improve your experience. Okay? So, yes, another question?
Before you start with your talk, I saw GNU Emacs. So at where I'm working, we are relatively heavy users of Emacs, but the Ada mode of Emacs is, let's say, a little bit
wonky.
In a weak state, I would say. And there is no maintainer anymore, to my knowledge. And so I'm wondering what's going on in this area, in particular to have a proper link between Emacs and the Ada core language. For example, so what is the state there? Is there someone working on that?
So the question was, for the online people, what's the state of Ada mode in Emacs, because it's a little bit broken? And the answer is yes, the maintainer is very old and he decided to step down. And a lot of people don't know the Ada mode was one of the first modes to take place. and hasn't been, and its architecture is ancient. It's huge, actually. It's one of the biggest modes of the Emacs ecosystem. We are updating it to have the new three-seater system, to use the new three-seater system in Emacs. There is a lighter version, and we are working for new maintainers. Also, I also would like to encourage people to use the new Ada language server, the ALS, using the new Microsoft technology for language servers, which is available. You can just install it with Alure and get started with your favorite editor. So if your editor supports the language server, which most editors do nowadays, including Emacs, you can use it. The ALS has a bit of a few bugs in it too. It's fairly new. The guy maintaining it is trying not to get killed by missiles in Ukraine. Luckily, things are working. Another thing I forgot to mention with NVIDIA, the reason I added NVIDIA here, it's not because it's a big, large company. It is. It's because they make it public, that they use Ada. One of the biggest issues, and I'm trying to change that, a lot of people that use Ada don't communicate that they use Ada, and they don't want people knowing that they use Ada. Missiles, anti-air missiles in Ukraine, some of them are developed in Ada from people in Sweden. Well, financial systems also use Ada, but they don't publicize it. They don't want people knowing that they use Ada. It's a bit of a problem. I'm trying to help that. So just as an added bonus on that. So we have people working on that, and things are slowly moving. So be patient, and we're looking for developers. That's mostly it. We are the Ada community, that's an open source community. It's growing slowly because the company, especially some companies, want to take a back seat and they want the community to come in, and that takes time. So sorry about that, but hopefully it's a temporary, it's a transition just. And we have 1 more minute if someone has any questions. If not, yes. So the question is, what's the marketing story of Ada compared to Rust? I encourage you to stay here for the rest of the day. You just read the code. One of the beautiful things, and the thing that sold me about Ada, is you don't have to know Ada. You can read Ada, even advanced code. That's impressive. And I have a later talk that's quite advanced, and I encourage you to watch it because even advanced concepts are very easy to understand. We have formal proofs, and that's way more powerful than just memory safety. People don't realize that, and there is a reason why safety critical systems still use Ada. And NVIDIA, I encourage you to watch the video from NVIDIA why they didn't turn to Rust and they decided to go with Ada. And that's one of the things. Don't believe my words. Believe the people that actually have invested millions in these things. They have even more incentives. So it's readability. It's actual, like, true correctness, not just memory correctness, and it's very stable syntax. You can just get Ada 83, and it works today. It's not broken. It has a slower pace of development. The features, there is a wonderful talk from past Ada DevRoom from 2021 from Paul Jarrett, where he compares C++, the features of C++ and Ada. And one of the greatest points he makes is the composability of the language. It has a lot of keywords. Some people think it's very verbose, but every keyword has its meaning, and it's very concise. And you can then build your own infrastructure on top of them. And that is a wonderful thing instead of like Rust, where you have a lot of like optionals and a lot of syntax to do a lot of stuff, but the language is all over the place. And you have like 7, 8 different types of strings. In Ada we only have 2. Bounded, normal strings and unbounded ones. So I encourage you to try the language. So time's up. Yes, and we are working on that. At Rust, I have to say they are doing a wonderful job in terms of communication, tutorials, and improvements towards visibility. And we are working on that. So thank you. There you have. Perfect. And HDMI. So you can
share as well?
Yes.
Yep.
I'll go.
Because you're the main guy.
Oh, yeah.
Is this you?
Later.
I put it on the next to the door.
We want to leave it.
You should have a schedule.
Ça poi le minimum.
Schedule needs to be taped to the door.
Peut-être vraiment check ça. I took the one that check that also.
And this as well.
Let me see here. Put this back in the file. So we don't use them. Let's try a different resolution.
Do you have the mic?
I do have the mic.
Can you,
Testing, 1, 2, 3.
can you, I will try something. Can you speak?
Testing, 1, 2, 3. Testing, 1, 2, 3. Testing, 1, 2. Uh-oh. Testing, 1, 2, 3.
Ако намалим тук.
Testing, 1, 2, 3. Testing, 1, 2, 3.
Is that better?
Testing, 1, 2, 3. Testing, 1, 2, 3. Cool. Testing, 1, 2, 3. Let's try a different. Testing, 1, 2, 3. Yeah, testing. This is how I'm going to be speaking. Testing, 1, 2, 3. Testing, 1, 2, 3. Testing, 1, 2, 3. I can adjust the mic. Testing, 1. Okay, great. Now, if I can get this to work.
Okay. You won't be visible if you stand up.
Yeah, I'll move over. I was trying to get the projector to work.
The presentation is...
Oh dear. That is strange. I might have to... Huh. Let's try a different resolution.
You can go to HDMI adapter.
Where is the mic?
Yeah, I've got the microphone. Okay. Does anybody have a spare USB dongle or USB? Oh, here we go. Let's try this one.
This is micro HDMI.
Oh, that's my... Yep, oh, that's good. There we go. Okay.
Okay, yeah.
Oops, one more. One more moment. Technical difficulties. Okay. I think I just need to... All right. Almost there. Let's see here. Okay. Gotcha. There we go. All right. Sorry about that. get started. Hi everybody, I'm AJ, and I'm kind of obsessed with Ada. So it started around 16 years ago when I first picked up an old Ada 95 book at my university library, and I was immediately hooked. I had just learned C++ the previous semester, and with summer starting, I was trying to learn as many languages as I could. I dug into everything from Forth to COBOL, but Ada's focus on structure and safety had always stuck with me. I would annoy my friends and colleagues who always worked in like C and later Python and Go, trying to argue in favor of Ada. In my defense, I fell in love with the language, the expressive syntax, and the powerful type system. Since I could build constraints directly into the data structure, I can code my program in a declarative way without ever worrying about the underlying architecture. If low-level features were needed, well, that's fine too. I could even define certain data types by how many bits it should have or where in memory it should go. I could go on all day about Ada's features, from its built-in multi-threading with text-safe objects to enforcing readable and correct code through its syntax, but this is a lightning talk, and, well, now I've got less than 15 minutes. About 7 years ago, I came across a post on Reddit called Going All In with Ada. It was posted by an architect who discovered Ada while nerding out on aviation. With no programming background, he taught himself to code in Ada and started a software company. This was kind of the push I needed to put my money where my mouth is and practice what I preached. I bought a copy of John Barnes' Programming in Ada 2012 and decided that any coding I do moving forward will be written in Ada. In the following years, I would watch another language focused on safety, memory safety be exact, quickly become one of the fastest rising languages with an ever-growing community. Worst of all, at the same time this language was rising, I saw Ada shrinking every single year. Yes, I'm talking about Rust. Those very same friends who weren't interested in Ada, they embraced Rust fully. So it seemed to be the answer that they were waiting for. So I had to ask myself, why not Ada? I spoke to several of those friends over what they found great about Rust and what issues they ran into with Ada, and they gave me some feedback. So, there we go. So first, Rust was very easy to install. You could simply visit rustup.rs, run a command. Congratulations, you now have cargo. Ada, on the other hand, well, what license do I use? What is NAT Pro? Community Edition? What's that? What runtime license? Rust, it was easy to start a new project. You just open up cargo, type in cargo new foo, cd foo, cargo build. And congratulations, now you have a project. Library, there's an ecosystem with crates.io, and the library and the ease of creating a project, Alir actually makes that pretty easy now, so that's a solved problem, but more on that later. Rust also had accessible documentation, vibrant community, and even an absolute beginner can start using Rust with almost no barrier to entry. Come on. Uh-oh. Okay. There we go. So, like I said, many of these points have been addressed in the 2020s for Ada, with the retirement of Community Edition and the introduction to Alir. However, when I see someone trying to learn Ada with no prior knowledge, Alir's almost never mentioned, and the first impression they get with Ada is getting tied up with NatMake or GPR build. For those that do come across Alir, they're either using older versions from their package manager, or they have to go through the manual installation process, such as adding things to path and such. And that's why I wrote Get Ada, to try and try to lower that barrier to entry as easy as possible, essentially to be like how RustUp works in Rust. So in this next video, I can show you how I used Get Ada to go from having absolutely nothing Ada related on my Mac to having a fully working compiled version of Hello World in less than 2 minutes. So I visit getada.dev. I just copy and paste this command in my terminal. It prompts me. I select yes. It downloads and installs Alere. I have to either restart my terminal or copy and paste this environmental command to add it to path or make sure it's added to path. Then I cd to projects, start a new project, ALR init bin dev hello world, jump in. I'm just using the defaults here. And then it automatically goes out, grabs the latest version of NAT, adds it to my computer. And now I have a project. It sets up a little shell project for me automatically. So now I just have to edit this file here. I can add my quick hello world. And then I save, I run ALR build, it compiles it, and it adds it to the binary directory, bin directory, and I do hello bin, hello world, and it runs. And that's it. Does anyone have any questions? Sure.
You mentioned that people use older builds from package managers.
Yes.
What's the hold-up of just introducing what you just showed as a package into those package managers?
Yeah, so for the listeners, asking about saying there were older versions of the package manager, and what was the second part?
What is the hold-up of just...
What's the hold-up of just using the one in the package manager? So,
just getting what you just showed us
yep.
into the package.
Oh, just getting what in? Haven't looked into getting get Ada into the package managers yet. Ideally, that would be the next good step to do. Yeah, the reason Allure being in the package manager is causing issues is because older versions of Allure are not getting updated, and they're not. There's like missing features, and there's issues with the index and stuff. But get Ada into the package manager would actually make things pretty streamlined, I think. Yes.
Are there any defaults or tooling around the unit test? Basically, how much harder it is to get the first unit test?
Yes. So there's a bit. I'm having everything automated in GitHub Actions, and as soon as something's pushed, it is recompiled and tested on all of the available platforms, which except for ARM, which is coming soon. But yeah, it was everything. It doesn't have a new release until everything is passing all of those tests.
So I also mean, is there any testing framework or a popular one, say like JUnit, right? I don't have to think what do I pick to run my unit tests. Like this for Ada.
I'm not too familiar with the unit tests for Ada. I know there's AUnit. There's a whole library built around unit testing for framework for Ada, and I think that can be included in Alere. I think you just do ALR with a unit, and it pulls in the unit testing library. And you can also bring in GNAT Prove and Spark and all of that. So anything that's available in Ada is generally available in Alere. And you can just go to alere.ada.dev/crates.html, and there's tons of libraries that are already submitted to the Alere index. And it's super easy to add a library. You just ALR with library name, and it pulls it all in, including the unit test functionality. Any questions?
There is a comment online, and it says, not a question, but there is some irony when the suggested way to install a language focused on safety is to curl some string pipe into.
That's fair. That's fair. You can download and run get Ada from the GitHub repo if you don't want to pipe curl to shell. I'm pretty much following what RustUp is using to get that, and for, I guess, getting, I mean, it's valid for people who are security conscious. They don't want to do that. You can just load the file and read it yourself. It's all it's doing is pulling the installer and running it in a temporary directory. But any other questions or comments? Great. Well, thank you.
we now have a 5-minute pause if you want to go in or out. And also, don't forget, if you want, you can grab some stickers if you like them.
Muted.
No.
Okay. Do you hear me? Okay, good. Good morning, everybody. I will show you how I program a BZIP2 data compression encoder in Ada from scratch during 2 rainy weekends. So my motivation were fun, first of all, a challenge, a bit of a warm-up for Advent of Code, the latest. And on a more serious note, I wanted to fill a gap in the zip Ada library, which is the BZIP2 encoder was missing. There was a decoder right to the yellow cell, but there was no encoder. It was absolutely, this gap needed to be filled. And my expectations were quite low because this BZIP2 scheme from experience compresses not a lot of kind of files better than, for instance, LZMA. The algorithm is mostly mechanical, so on most steps you have only one way to encode the data, but not all steps. And BZIP2 is actually a weakened version of first BZIP, so it's very old. And at the time there were patents about arithmetic encoding, and the author had to change to Huffman trees. But the results of my programming exercise were absolutely surprising. So I got 2 very good surprises. Of course, I keep them for the end. So I will explain you the BZIP2 compression scheme in 15 minutes. Some people are skeptical. No, actually, the BZIP2 is completely unusual as a compression scheme. It's super simple. I promise you it's simple. First of all, it's not a streaming adaptive scheme. It doesn't use sophisticated technique. You have twice run length encoding, which is the most trivial way of compressing data, just a repeated sequence of exactly the same symbols, and a few other techniques. So once you have treated your block on step 2, you output everything in one go. So it's basically an offline algorithm. You see in the green box the Ada code. Of course, some is missing in the red ellipses, a few hundred of lines. But basically, you have all the steps with these codes. It's super simple. For instance, one of the run length encoding, you don't even have, it's very smart, you don't even have a special symbol to say, now there is a run. Automatically, after 4 symbols, you have an extra byte saying, you have a run, and with the length, the extra length. So it's very smart, and you have again from the 6th symbol. Now, the core of the BZIP2 algorithm is a mysterious transform called Burroughs-Wheeler, which is a bit, the history is also funny. I don't go into details, but basically you take the blue message on the top left, you shift it, as you see in the left box, you sort all the lines. The right box contains the result of the sorting, and you output the red column, the rightmost column. That's the output of this transform. That's as simple as it is. the fascinating thing is that you can reverse this transform. So this letter soup on the right can be reversed if you know the index of the original sentence. So basically you don't compress anything, and you also have an extra information which is an integer. And you wonder, but what does it have to do with data compression? The data on the right, the red thing, it doesn't look in this example more compressed or compressible or whatever than the blue message. But let's have a look on a larger example. So here I take the source code of the encoder itself as a test data, and you see there are lots of repetition with this transform. And that's, of course, the reason you can do compression with that. You have lots of repetition, so you can do, again, run length encoding, and before the run length encoding, you do move to front transform, which is, again, super simple. Imagine you have a card deck which is sorted at the beginning, and if you take the card number 6, you have the index number 6 because the original sorting. And after it becomes a bit more complicated because the cards are progressively shuffled. But the interesting feature, the cards that appear more often have a lower index, and that's very prone to compression. For instance, card number 6 appears after a third time, the index is lower. And the final step, here it's a bit smarter, it's more difficult. It's the entropy coding, so it's compression with Huffman trees. So the author of this scheme had the bright idea to not to have a single entropy coder. You can choose between 2 to 6 Huffman trees, which are completely freely defined. Of course, you try to do it efficiently. And also, for each group of 50 symbols, you can allocate one of these 2 to 6 trees. So here you have lots of room for optimization. It's where the elements are squeezed properly. So the results of my exercise after the last rainy Sunday, to say it politely, I would say, what the, okay, but there's a camera, so yeah, holy cow. So on the third bar, you see the compression of the original BZIP2 scheme, the one that you find everywhere, especially on Linux, through the zip utility. It's using this algorithm if you take the right switch. In the middle, you have 7-zip. Everybody use 7-zip. So if you tell it, take BZIP2 encoding, here you go. And on the left, here is the compression with the new encoder I just wrote. So I was totally surprised that it compressed better than these tools that are developed for decades. To be mentioned, again, BZIP2 is very good for human written texts, like ebooks, and also source code. Of course, not automatically generated source code, but human written source code. and less good for other things. But for these things, it's very good in general, and surprisingly, my implementation is better. And the second surprise, what happens if you have a mix of different data type? So you have many benchmark test data called corpus, like the classic Canterbury, where you have images and other kind of things, and also source code and ebooks. And the second surprise was that even in this context, by using the zip Ada preselection option, which picks the right algorithm depending on the data type, the overall archive size is smaller than not only 7-zip with the maximum compression for a zip archive, but also the second bar on the bottom box with the 7Z archive, which combines all the files together. So it was also a super rejoicing surprise there. And yeah, so what are the, since we are in the Ada DevRoom, what are the benefits of Ada, except that apparently you can make a winning encoder in 2 days, in 3 days, so quickly. I would say regarding data compression, it's very difficult to debug. If you have a bug, you almost have to start from scratch, because the output is random. So a wrong random doesn't look like better than or worse than the good random data. And really, Ada does its best to do the things right the first time. It finds tons of dumb mistakes, programming mistakes, and if you use the customizable, you can create as many custom types as you want. So I've listed range types in the box here, and also if you use these types, you cannot mix too easily an index with an element, and these kind of mistakes you sometimes do. Plus, you can define subtypes, so it's range types with a very tailor-made range. And in compression, you always have very strictly delimited ranges, so it's a perfect fit for that. And in the two of the types listed there are data dependent, so it depends on the data you are compressing. So it's kind of, you actually have dynamic types in Ada, so they depend on some data features. So yeah, that's it. Questions? Yeah.
Runtime and memory usage differ?
So I was runtime and memory usage. I was not too. I didn't try to save too much in memory. So you have a few megabytes of memory usage. You could squeeze it to perhaps 1 megabyte by reusing things. But nowadays, a few megabytes, it's not so. Yeah.
When I'm talking about memory usage without 1 how does it scale, and not so much about the fixed overhead, but if I give you a 2 gigabyte file, how much?
Yeah. So how does it scale? This format is by design limited to 900 kilobytes. Because there is a reason. Because you remember the strings that were sorted. The sorting of these strings explodes with the size. So you have to slice your data into maximum 900 kilobytes. So it's very easy with memory. You can allocate as you want. You don't need to spare too much. And runtime, there is some improvements to do. I'm using the standard Ada sorting, and I should use more specialized sorting for that. But it's for later. Yeah. It runs conveniently fast on most data, I would say. Yeah. Similar to 7-zip.
When you say 900 kilobytes, it's the window, right?
Yeah.
Sliding window.
So, no, it's not. You take the first 900 kilobytes, you process it, you take the next, and so on. It's very... Yeah. It's very special. It's not a streaming compression scheme. It's really, you take a block, you process it offline, you output it, and so on and so on. Yeah, question?
This first plot you showed, the y-axis, what does it represent?
Sorry, the white?
The first plot you showed, the y-axis, what does it represent?
Sorry,
the first plot you showed, the y-axis, what
the
does it
white
represent?
axis. Ah, the Y. Ah, it's the size. They just on the. So
Yes,
this one, it's just bytes, compressed bytes. Of course, it doesn't go from 0, but you cannot compress to 0 as well. So. So, 1 minute left. So I have to wait 1 minute. No. Okay. Yeah. Okay. So I can start with the next one, or
No more questions? Okay, thank you.
I can start that. Okay.
So we'll want to wait 2 minutes before you start for the video feed.
Okay, so yeah, because I'm a bit in...
And then the next one starts at...
Yes, I will let you know when you go.
Okay, yeah, so I'm not late. Yeah, okay. Yeah, it's okay.
If you want to...
Okay, Okay, so let's start. So next topic, nothing about compression or whatever. Ada and mini Ada, a solution to the two-language problem. So what is this two-language problem? So a bit everywhere where programming is used, you see a similar setup. You have people using a typically a scripting language for prototyping, for processing data, for generating code or whatever else, or do some simulation or shell scripts or for studying things and so on and so on. Typically, you have things like Python or MATLAB or whatever on the left side. On the right side, you have typically C++, Ada, and other statically typed languages. They are there for performance. And as long as people work in their worlds separately, it's okay. But more than often, they have to interact. And then there is a problem because there is this language wall. And it's something that many people are trying to break this wall. And a solution that I want to present is to use Ada, but in perhaps, depending on how the context, in two different forms. Use Ada on both sides, so you have some flexibility between the prototyping and the productive application. And of course, on some things like SQL, you can keep it as such. It's not a problem to have the second wall there. It's not an issue. Oops. Yes. So one thing you see in the professional world or academic as well, everywhere, you have one team which is doing a sketch in pseudocode or a prototype in a scripting language. It can be MATLAB, for instance. And they are working in a bit in their bubble, basically. And the implementation is left to other people who are using another language, so the language Y, for instance. So they have to translate everything, and suddenly the team X wants to make a modification. They have to call the team Y to try to adapt to this modification. And as you can guess, it's a very tedious, complex, and inefficient process. So here, a solution, depending on where, what, and depending on the context, would be to use my small hack Ada compiler for X, for prototyping, because you have a very quick compile run cycle. Basically, you don't see the compilation, it runs immediately. And use full Ada as a Y language, so for the write. Another situation you see is you have both languages. You have typically you have a team doing Python or R, for instance. Another team doing, let's say, C++. And a third team doing the interface between both, or translating bits of X into Y and maintaining painfully the interface. So it's a bit less complex, but it's a bit more complicated in terms of teams, because you need basically more or less 3 teams. So here, a solution would be to use full Ada everywhere, because it's very accessible also for engineers, with people with no programming training, or hack. The hack compiler for the X language, and for Y you would have for the heavy lifting you would have would use GNAT essentially. I say full Ada because there are other Ada compilers. You have something called Object Ada, which is full Ada 2012, so and Apex Ada at least. So actually you have 3 Ada 2012 plus compilers available. And the third case is embedding. So you have typically industrial software or a game, embedding a kind of scripting mechanism in order to do some live configuration, or for a game you can spawn some monsters or whatever. And yeah, so the typical X language is, as usual, C++ for X, and Y can be Python or Lua. You see often Lua as a mini language which is embedded in a software. So yeah, for a game it's not a problem because people don't know to struggle with C++. They play their game and they program their Lua script. But for an internal software, it's a bit more difficult because you need normally the knowledge of both languages. It's not a mass product, so it becomes again a bit difficult. The developers in the X language need to explain things to the Y people and so on, and they want some new features, and it's a bit tedious. And the languages are, as in the two other cases, not compatible, which is not good. So here, the solution is to embed the hack Ada compiler. So it's a mini compiler I'm maintaining and developing into the full Ada application. So I make a little, yeah, we'll see a demo, but just I summarize advantages. So it's the same language. So you have more or less the same people who can understand the application and the scripts, basically. And you can even share the same source code between both. That's a very powerful feature. You have the same type system. So how does how does the embedding of hack look like in an application? So here you have probably the simplest usable way of embedding the hack compiler into an Ada main program. So you have builds from a command line argument file name, and if the build is successful, you run the program. So here you have a very small example where you can run an Ada program from another Ada program. But it will be better to see a live demo, so I do it. Next. So here you have GNAT Studio, the programming studio provided by AdaCore for the GNAT compiler. And here,
Can you increase the contrast?
Yeah, of course. A bit like that. Or perhaps I change the resolution. No, I think it's okay. Is everybody able to read more or less? I give a try. Should be okay. So but I will have to scroll a bit more. So here you have the main full Ada program. The little difficulty is, since you have Ada in Ada and not completely different languages, I have to explain which Ada is which. It's the backside of the power of Ada in this context. So, yeah, here I have an almost infinite loop. Okay, it will terminate with the last positive number, but you won't see it. And each time it builds a mini hack program, which is called exchange hackside simple. Hopefully it's simple enough. And then it's run, and there's a pause in order to protect your eyes. But here you have a callback mechanism which is initiated. So I show you very quickly. So you have, so it's a full Ada callback, which is registered, which is doing something with data. So you will see there's a data exchange between the callback and hack. And this callback, so here you have the pointer to the callback, and it is registered. Okay? And now the hack program, I open in another editor just to make it more, I have to, yeah, that's should be readable enough. Of course, if I try to run it, it doesn't work as a main, because I have to connect the callback. So you have a pragma import aspects with the callback here. And yeah, this. So this callback will put, okay, the usage of I in both places, so I change it. It's more readable like that. Oh, fuck. Yeah, no error. Okay, it's okay. 3 minutes is perfect. I will have done the demo in the meantime. So I put the value 1, 2, 3, 4 into the I parameter. It's very simple. And I see the callback on the GNAT side. So before the call, the value is 9876, and after it will have changed, or vice versa. Okay. No, it's after. Okay, you will see with the demo how it works. So yeah, here, so you have this quasi-infinite loop. So each time the native is calling hack, which is calling native. It's a bit complicated, but you see the value 1, 2, 3, 4, 9, 8, 7, 6. And I can really change live the program. So you have the GNAT program running, still running, and I put 10, for instance. So you see the newly compiled program gives 10 as a result, or you can put another message, hello, whoops, FOSDEM, and just save it. hello FOSDEM. Yeah. So, questions? No question. Yeah.
Is there a mechanism for caching the compiled version?
Slowly, I'm not so good
Is
with.
there a mechanism to cache the compiled version, so unless the source changes that I reuse as much?
It's not. The question is the source cached in any way? Huh? Yeah. No, it's read from the file, but you could. The hack compiler is able to read from any stream possible. So you could cache, you can read from memory or whatever. Other questions? So. A repo? Repo?
Read without print loop. That's what scripting programmers, they want to write, very simple.
Can you use hack as a scripting tool? Yeah, I do it all the time. Yeah.
That would be a better demo.
Yeah.
More compelling.
For the next time, yes. Other questions?
So just to get straight, this HAC is basically a bytecode compiler, I assume?
Yeah.
And so it's like probably an order of magnitude.
So the question is the hack compiler a bytecode compiler which interprets the bytecode? Yes. But actually there is a it can also output native code, but it's work in progress. But the thing which is working is the bytecode. But it's actually multi-target.
Okay, so there's no real just-in-time compilation yet?
Yeah, it's just compiled at every cycle. Yeah.
I mean by a just-in-time compilation that if you notice that some code is running hot, it takes the bytecode and optimizes it and produces machine code. Because we have that in Lua. We have Lua 2. And it can be pretty fast.
Okay, so yeah. So the question is there a just-in-time compilation? Answer, not yet.
Time's up. So thank you, Gautier. Now for the next talk. Thank you. Sorry to have both talks back to back. Yes, it's just the next. Yes. Okay. Yes, we need to connect it here to the back, to the HDMI. No, it's not. Oh no, that's the charger. That's the power.
We should take a picture after the next slide, after the next session.
Huh?
We have 5 minutes after the next session.
Ah, okay.
Can you announce it?
Okay, so let me refresh. So this is working, seems like it. Okay. So we are on time, I believe.
1 minute.
1 minute, doesn't matter. So let's get started directly, and we are going to talk about some very technical topics. So I do expect some programming knowledge. Hopefully I will make everything understandable, but if I don't, please feel free to ask questions afterwards, and if I make some mistakes, feel free to correct me on the spot so that the recording gets the correct data. So, understanding liquid types, contracts, and formal verification, all with Ada. Nonetheless, even though this presentation is going to be using Ada Spark, I will explain the difference later, all the points I'm going to make, they should be translatable to other languages that also support these features, okay? That's my goal, that's the main goal, to express these concepts in a general manner. And the examples will be practical. I'm not a mathematician, I'm actually a mechanical engineer working in the nuclear sector. These things are not meant to I'm not going to be too precise with whether something's a discrete type, a liquid type, whatever, no. Things are going to be practical, and I'm going to show a bit of code. And the reason I'm going to do that is because of Ada. Ada is very readable, so I hope that everybody, just by reading the code, is able to understand all the concepts I'm about to introduce. Also, very interesting note, all the code I'm going to show you is valid Ada 2012. I'm 27 years old. That standard came 13 years ago. Half my life have these features been available. If you think these concepts, these programming concepts are new, are fresh, no, they are not. They are very old. It's just that most programming languages just simply don't support them, which is kind of a sad thing. So let's go directly into types. What are types? Normally when we think about types, we think about integers, arrays, pointers, voids, whatever, you know, data. Types, normally we think of them as data, and we understand them as data at the CPU level. 8 bits here, 64 bits there, and they are floating points. Normally we focus on the information at the CPU, GPU, memory level. That's why higher level languages, they don't think of they normally don't have types, or they just have numbers, and they abstract that information away. However, some newer programming languages have realized that types can be useful, very useful actually. Take Rust as an example, with their optional type. They are using types not to just describe data, but to describe program flow. In the case of the optional type, it describes something that may get you some data, or something that may get you no data. For example, a network request. If you make a network request and it fails, you get nothing in return. And you can model that behavior at the type system in your language. And the compiler will force you to check those two different stages so that you don't make mistakes, which is great. But when we talk only about data, only about information, most programming languages still default to generate bits in your CPU, which is kind of a shame. So when we ask ourselves questions like, hey, this variable, great, it's an unsigned 8-bit integer, and its value is 11, is that a good grade for a student to get in a test? Is that a bad grade? We don't know. It's just an unsigned 8-bit integer, and it has the value of 11. French people will say, yes, that's a passing grade. German people or Spanish people will say, no, that's not possible. And that's the problem. We have no context for our data. People think, oh, low level, you have to work directly against the CPU, which is not true. And in Ada, the type system, I believe these are called discriminated types or discrete, whatever. In Ada, we describe the real world data we actually work with. That is a huge improvement. So we can describe what is good data, what's not bad, what's bad data. We can have a tower of types. For example, in this case, the grade is a number from 0 to 10, and we have a subtype, which is just a normal type that's completely compatible, failed grade, which is from 0 to 4. So if I ask you, is 3 a passing or failing grade, you can tell me the answer just by looking at the information. We can refine things, obviously. This is the Spanish grading system, so we have decimal point numbers. Yes, we have decimal point numbers in Ada. This is a fixed point type. Most modern programming languages don't support these types, which is kind of a huge shame, especially if you're working with money and things like that. Very sad. And this leads, and a lot of people see this and they say, oh, Ada is very verbose. I just need an unsigned 8-bit integer. But the thing is, this is useful because we can do stuff like this. A, is 3.38 in a failed grade? And the answer is yes. We can reason about our information at the code level. Just think about data validation. It just becomes trivial. It's wonderful. But of course, some people may say, hey, what about efficiency? Isn't Ada supposed to be a low-level programming language for embedded systems? And the thing is, the compiler does the heavy lifting for us. And if you want to have control of the bit level, and I said bit level, not byte level, you can do that very easily in Ada. If I have time, I have some backup slides for that. And you can play around with your code in the compiler explorer and see if the assembly is indeed efficient or not. It is, I can tell you that. But careful with your optimization flags, by the way. Nonetheless, someone may ask a question. Hey, Fer, you're talking about modeling real-world data and ranges and things like that. Good, they are good, but what about some other data, some more complex data, some more refined data, like even numbers or prime numbers? They cannot be represented with a generic range. How does Ada do any of that? Well, let's understand the data we are trying to represent. Normally, data has some kind of definition. In the case of even numbers or prime numbers, their definition would be, for even numbers, for example, numbers that are divisible by 2. And we can very easily transform any definition into an if statement. If a number is divisible by 2, then it is a prime number. Same thing for prime numbers, although the definition is a little bit more complex. If a number is divisible, it's only divisible by 1 and itself, then it is a prime number. We can transform pretty much any definition into a logical statement. Can we put that logic, that reasoning, as part of our type definition? Can we make types with logic attached to them? Types with logic, logically qualified, liquid types. So that's it. Liquid types are types with logic in a simple way. Okay, I don't want to get too academic about it. So how would we go about it? Well, let's say even numbers are just numbers, but we now need to express what we just said. And in Ada, we are going to do that with the with keyword, dynamic predicate. Predicates are just a way of introducing logic to stuff. And the with keyword is an incredibly powerful Ada keyword I don't want to explain. But nonetheless, all different languages have their own kind of syntax. One of the reasons I'm using Ada to explain these topics, it's very readable. Some other languages, I encourage you to take a look at them. They tend to be very symbolic heavy, syntax heavy. In Ada, it's just English prose. So we just say that. Dynamic predicate, and we write down the definition of our data. Even modulo 2, so when we take the remainder of the division, we get 0. Now we have truly an even number, and we can get the odd numbers basically for free with that. What about prime numbers? Well, and the things we just did before, like testing for our data and data validation, now become intrinsic to the program flow of our execution. So if I say my even number is 2, yes, everything's fine. But if I say, hey, I'm going to assign the value 3 to my even variable, oh no. If you compile Ada with assertions enabled, you will get a runtime exception. In Spark, as we will see in formal proofs, your code will not even compile. Oh, that's very interesting. So now incorrect program state truly becomes incorrect. And we can still do testing for validity of data. Is 3 in even? The answer is false. Once again, you can test this in Compiler Explorer if you want. What about prime numbers? Well, we just write the definition out. Obviously, it's a little bit more refined. Obviously, it's a little bit more complex. I will let you check whether that definition is correct. And it is, by the way, using some funny Ada. Ada doesn't have a lot of undefined behavior, so even incorrect ranges are defined to have a behavior. But anyway. So, and the thing is, we don't even have to express all the properties of our data as part of our type definition. If you have your typical isValidData function or validate_data functions, you can just pop them into your definition, into your predicates. You don't even have to rewrite your code. Just pop them in, and that's it. Also, liquid types in Ada are known as type contracts. In other languages, they are also known as that. Just letting you know. But I know what you're thinking. Hey, Fernando, this is useful for academics, and that's why liquid types are used by academics. Just look at your examples. Even numbers, prime numbers. Are we cryptographers? This is useless for real-world programming because real-world programmers do other stuff. Well, let's take a look at this. Imagine we have a data structure and we are tracking some temperature. It could be some logging system of your server. It could be a financial institution tracking some stock prices. And we have a time frame, for example, days. It could be milliseconds. It could be your, I don't know, measuring some electricity in your outlet every hour, whatever. And we have a high value, current value, and low value. We always want to keep track of the current state and the bounds of our data. And somewhere in the code, maybe written by us or by someone else, we just want to update the current value, and we do so. No? That's the very typical thing. We are just doing an assignment. Oh no, we just introduced a bug. Can you tell? Just doing an assignment and created a data corruption bug because we forgot to update our values. What if the temperature we're measuring in our garden, the current temperature is, I don't know, 30, and we didn't update the high value from before, which was maybe 28? Does it make sense to have a data structure whose high value is 28, the current value is 30, and the lower value is, I don't know, 25? No, we just corrupted our data structure. Very simply, just by doing a simple assignment. And here's the thing, if we know the properties of our data, that the high value has to always be high, the current, higher than the current value, and the current value has to always be greater or equal to the lower value, why don't we write that down? That's just a liquid type. If we express the nature of our data, how our data behaves or is related to each other, we just write it down. And it's not a comment. This is actual code. And if you compile Ada with assertions, you will get a runtime error once you return the data. Ada allows intermediate incorrect data states. In Spark, you are not allowed to do that, and you will get a proof error if you write this code. What about sorting algorithms, or searching algorithms that are very efficient and they need to work on sorted data? How can we represent that? In most programming languages, you just cannot. You just pass a generic array and you hope it's sorted. In good programming, you create a new type that's sorted and it's only returned by procedures that use sorted data. But we can do better. We can express the nature of sorted data directly as the type definition with a liquid type. We introduce the logic of what it means to be sorted as part of the type definition. That's wonderful. That's very powerful. And I want to address one big comment that I know I'm going to get in the questions and answers. Hey, Fernando, your example with the data, with the temperature, yeah, that has been solved since like the 80s by using the getter and setter pattern in object-oriented. If your data has some kind of behavior, you just make it private. You don't let people modify it. And you create a function that does the correct modification to your data. Liquid types are a nothing border. But here's the thing. Yes, you would be right, and this example would indeed give you better code reuse, actually. But here's the thing. For example, in this case, object-oriented programming, which is how most people would do that today, it's a whole new programming paradigm. Liquid types are your types that have been enhanced. It hides the data, which basically nukes the three things you do with data: read, write, and modify. You just basically destroyed the nature of data. And it requires you to create an API. So now the problem of handling data, it's on you. And here's the thing. Is that setter function blocking? Is it writing to a file? That's forbidden in a lot of cases for high-performance computing. Did you know that? Oh, did the person that called the setter function knew that? Was that documented? If it wasn't, you have caused a bunch of other issues because normally the APIs are opaque. People don't look how they are implemented, and that's a problem. Liquid types are just types, powerful types, but just types. They are wonderful for instrumenting and debugging your code. I actually can tell you that I enjoy debugging Ada code, which Doesn't happen with any other language. And they will allow us to do formal verification, as I will explain later. And here's the thing, the wonderful thing about liquid types. They can just coexist with the rest of other programming paradigms. If you do OOP functional, they just refer to data. So anything that works with data, all programming paradigms, basically, they can just use it. They are not incompatible. And if in case you don't like this example in Ada, you can use the limited keyword, whatever. It is a great language. So let's go directly into functional contracts. And I'm going to be much faster here because here's the thing. What are programs? Programs are things that take some inputs, they process those inputs, and they generate some outputs. It can be a simple function, it can be a whole program, whatever. And we've been talking about data, about liquid types, about being declarative, about explaining what our data actually is. So we've been focusing on the inputs and the outputs, and about their properties. And here's the thing. Someone could ask the very simple question. Hey, could we apply the same principles, but instead of just data, the actual execution of our program? Can we do that? Can we add contracts to our code, types to our code, just like we did with types? And the answer is yes, that's functional contracts. So let's go directly to an example. Imagine we have a stack function, a stack package, where we can push data in and we can pop data out. Well, we all mostly know that that is dangerous. What happens if you push too much data into a stack? Well, you just cause a buffer overflow. What happens if you pop too much data into a stack? Well, underflow. How do we know what's the behavior of our functions when that happens, if that happens at all? Is it going to be prevented? Well, we would need to look into the functions and see if it's guarded or not, or what they are doing. Simple, if we are very worried about our users mistreating our functions or our data structures, we can do explicit guarding. And if someone tries to push too much data, we can say, hey, sorry, you cannot do that. And raise an exception, throw an exception. And that would be the case of Ada. But can we do better? Would it be correct to push more data than what's available? No. So why don't we say that as part of our function declaration? And we do that with functional contracts. So for example, in the push function, we say with, and once again, that keyword of Ada, pre. And pre is a short form of precondition. Before you are allowed to call this function, the stack must not be full. You are not allowed to call this function if the stack is full. Now we no longer have to do explicit checking in our function. That's guarded by the precondition, by all the properties that have to be true before the function gets executed. And we also have post conditions. What happens after the function has been called? In the case of the push function, well, the size of the stack must increase by 1. We must have added some data to our data structure. That seems obvious, but we don't even know how complex this function is or what it is doing in between. It could be a 3-line code bit, or it could be 5,000 lines of code. The malloc function of the glibc is about 5,000 lines of code. Did you know that? You thought it was just allocating some easy memory? No. These things can become extremely complex, and we don't care how complex they are. These properties are going to hold regardless of what you do. And we can annotate our code to do that. Also, if you would like to see the full answer to how to correctly program and stack, go to this repository, to the Platinum reusable stack. It's going to be a lot more than what you think. There is a lot of implicit behavior that people think and that needs to be guarded against. And I'm here just showing you preconditions, post-conditions, but real-world examples, they are complex, like global state contracts, like data dependency contracts, etc., etc. This is a real piece of example. What happens when we move some vector, some data to another place, to another vector? Well, these are all the things that need to hold. What happens when we do an insertion of one bit of data into a vector? You think that's simple? No. This code, by the way, is part of Spark formal containers. SparkLib is a formally verified library that you can just use. It's under Apache version 2. It's created by the people that do safety critical systems. These things are robust. They are not only memory safe, they are runtime, they have no runtime exceptions, no runtime issues, the correct handling of exceptions, everything. And talking about safety critical systems and things like that, wouldn't it be great if when we program something, we could know that it works as we expect it? Wouldn't it be great if when we program something, that we know that's doing what we hope to do, and that our clients can be sure that our program does what they want us to do? Wouldn't that be great even before we compile it? Like in Rust, like for example, the borrow checker will make sure that your program doesn't have any memory issues before it compiles it, because thanks to the borrow checker. Can we do all the checks before we compile that? Well, yes, but there are a lot of checks that we need to run, like memory errors, program flow errors, unexpected arithmetic errors. There is a lot that people just simply forget about. And can we prove that? Oh, provers, yes. Provers are basically compilers, but instead of creating assembly, they do all the checks I mentioned before, and they give you a thumbs up or a thumbs down, and they tell you whether your program has issues. And those issues can be very varied. Okay, so Rust borrow checker is, for example, a prover for correct memory management. And some other provers are better or worse at some different things. For example, TLA Plus, I've seen it being used more for like concurrency issues and things like that to detect those. And some provers are interactive, and they can walk you through your program and see if your program has some issues somewhere. Other provers, like Spark, which is the formal subset of Ada, which no longer is that much of a subset, will do so automatically. You just create your code, press a button, go and grab a coffee, and the prover will tell you, hey, you have an overflow here that you hadn't thought about. It's wonderful. And the way these things work is that they have some provers. The provers have some like programs known as SMT, theorem provers and things like that, like Z3, Alter Ego, CVC5, that they will get your code, they will analyze it, and they will tell you what could go wrong and things like that. So that's so do people actually use this in the real world? Most people think of, oh yes, like cryptography people, but real-world programmers don't need these techniques. But the answer is yes. People working on operating systems, when you need a reliable operating system that's just not going to break, you use these techniques. Liquid types, contracts, formal proofs. Of course, yes, cryptography. And one of the beautiful things about Ada, you can just work on it on embedded systems. A lot of other provers don't do that. And a lot of people are worried about performance. I would recommend you click on the Optimize for Performance link there. The guy that created this cryptographic library optimized it for performance while maintaining full proof correctness. But not only that, we use a ton of software daily that we are just not aware of, that we just expect to work. Are we sure it's just going to work? Our programs constantly parse JSON or XML. Are they going to work? How many times have we seen like security issues every time someone gives a malformed thing, a malformed JPEG or whatever? Quite okay image format that someone who we actually have here created a library that's formally verified to work on it. And it doesn't matter if you feed it incorrect data, an incorrect malformed image, it's just not going to break. It has been verified to that level. So, as a conclusion, liquid types and contracts allow us to express the properties and the nature of our code and our data, and they document and give meaning to our program at the code level. They serve as instrumentation, debuggability of our code, and they allow us to create very robust code and for proofs. And the formal provers, the formal verification of our code gives us the assurance that things are going to work as we expect them. They are going to be memory correct, they are going to have no exceptions, or if they have exceptions, that they are going to be handled correctly, that we are not going to have overflows, underflows, incorrect data management, etc. And they are wonderful, and especially Spark is a wonderful teacher because it has a counterexample flag that you can pass it and it will explain to you and walk you through how you got something wrong, which is wonderful. So, and just a bit about Ada. The reason I love Ada is because it has all these features I've mentioned, but you can also work on embedded systems with it, without operating systems. It supports a ton of architectures. It's low level, high level. It's very readable. You can interop with C code. It's wonderful. Yes, it's not perfect. Some issues are part of the community and the ecosystem. Some limitations are part of the language by design in order to get this robustness. But thank you. And are there any questions? How much time we have for those? 1 minute for questions. Oh, sorry about that. So thank you. So one quick question only. Yes?
When you use these features, to what degree are they verified at compile time versus at runtime?
Oh, so thank you. I mentioned that with Ada we have the beautiful thing of being able to. Let me repeat the question for the online people. What are the advantages and the differences of runtime and proof time of being able to select those? No.
What degree are they verified at runtime versus at compile time? Like.
What are the difference? So at runtime, in Ada you can select, if you just write your program, you can select full runtime correctness with that. It comes to a cost of the runtime, and Ada is a little bit lenient in some of the features you can do at runtime, like temporary, you can have temporary incorrect state if you so wish. In proof, provers are very strict. They will not allow you to have any intermediate incorrect data or state. And the runtime comes with the cost of the actual checks taking place at runtime. The size of the objects of the program is going to be larger, but you gain the debuggability and the traceability of your programs. That's why it's so easy to debug Ada. You just run it on a debugger. You just tell it to catch all assertions, to catch all exceptions, and you just close your eyes and let the debugger find it. But the prover, it will be a bit slower, noticeably slower. But once it's been proven, you can just trust the compilation of your code and go ahead with it, trusting it fully. So. There are no more time because we have an issue. Nonetheless, go ahead and write it to me in my email if you so want. And reminder, yes, Ada allows you to do very low level control of data. So, thank you. Do we have 5 minutes? No? Oli Scherer, no, the Rust guy.
Hello.
Hi, nice to meet you.
Nice to meet you. It was perfect that your talk was right before mine. I loved it, and
we did it on purpose.
Wonderful, thank you. Actually, I edited one of my slides while we were holding a talk just because of the slide that you showed. You don't see it.
And let me get this rid. Get rid of this. If you want a USB-C, we have an adapter for it. What?
No.
I'm the organizer.
Oh yeah. Sorry, I was in you.
So.
Okay, hello. No. Thanks. Is it working? Is it working? Cool. Hey everyone. I know my title is a little bit contentious maybe, but I'm a Rust developer. I'm allowed to say that. So who am I? I'm Oleo Blanco. I'm a Rust compiler developer, been now for 10 years. I came to Rust actually because of Ada. Before that I was doing Ada. And well, I've been doing Rust for 10 years now. My Ada is a little bit rusty, so bear with me. But I still code it every now and then. Anyway, this talk is not about Rust evangelism. It's the other way around more. It's just showing where we're currently at, because we've been doing a lot of work on getting Rust ready to be used in safety critical systems more. And yeah, so what have we been doing here? Bunch of topics. The unsafe keyword is the thing that's basically what in Ada is the, by convention, unchecked keyword. It's not really a keyword in Ada, but it's what you use to say, like, this thing is probably going to be dangerous. You should read the documentation, otherwise everything's going to blow up. We used to have some problems there in Rust. I think we've gotten through all of them now, so I'm going to just give a small intro there. Generic packages and modules, really cool in Ada. Rust, yeah, crickets. Safety certification, gonna go into details there. And we have contracts now. They're coming, they're not merged yet, fun, but the PR is open and almost ready to be merged. And subtypes, that's like kind of my baby that I've been working on for like whatever, 10 years. And we've gotten there, and so most of the talk is gonna be about subtyping. So unchecked versus unsafe. This is an example of code that you can write in Rust up to a few months ago that would have been totally fine compiling, and your program would have blown up because you created a malloc function, and malloc is a weak symbol in most code that you have out there. So if you just define a random malloc function with a literal symbol named malloc, you are now the owner of the malloc function, and whatever you write in there is malloc. And so if you just do something like random integer, well, your code is probably going to blow up because somebody's going to call malloc and dereference it, and well, bad things happen. Anyway, we fixed that. You now have to actually specify unsafe somewhere in there. Before you didn't have to, and blowing up a program without writing unsafe, yeah, no, not good. So we fixed that. Generic packages and modules. If you write a generic package in Rust, you get this error message. Like, it's so unsupported, even the diagnostics don't know what you're talking about. And Rust is actually famous for having good diagnostics, so yeah, anyway. I'm going to fix that soon, but we're just fixing the diagnostics, not actually implementing any feature. Safety certification. We are safety certified. We have a formal specification of, not formal, well, yeah, ferrocene. Ferrocene is used in safety critical systems. You're allowed to actually use your stuff in like cars and whatnot, at least in Germany now. I don't know about other countries. And there was some little bit of drama. Like, this used to be an interop with Ada core and Ferro Systems. It is now not. Drama happened, people quit, stuff like happened. I don't know if people quit because of this, but anyway, cool, we have this now, and it's still being developed to extend it, and it's always up to date with like the current Rust version, maybe like 6 weeks behind or something, but yeah. So, contracts. Contracts in Rust are similar to contracts before like Ada, what's it, 2012? When did we contract actually in the language? It's basically attributes, which are more similar to how you have random comments somewhere, except that the language will actually now check these attributes, and you can specify arbitrary pre- and post conditions. They're not actually formally checked in the way that Spark checks them, but we have the Kani formal checker for Rust, which is similar to, to Spark. It has all this SMT solvers in there. It gives you diagnostics. It creates counterexamples and whatnot. It's not fully complete yet, but it works for a lot of Rust code, and it's being used to like prove small Rust code as completely free of runtime exceptions. So that's cool. And well, the thing I actually want to talk to you all about after giving you the small update, pattern types. Pattern types in Rust are similar to Ada subtypes, except what we normally have in Rust is just like concrete types for like a non-zero U32. That's like an actual type in the standard library. You don't specify like, I just want my integer to not have 0. What you do is you use this built-in type, and you can't actually define these kind of types yourself. You can't do a non-10 U32. That just doesn't exist in Rust yet. And similar for pointers, there's a non-null generic type that you can define for any kind of pointer type, and it will give you a non-null pointer. But this is just a standard library type. It has a lot of magic in there to make it work, but it's not something you as a user will actually be defining yourself. Kind aside, so the rest of the stuff is actually well explainable. In Rust, type aliases are not strong. Not like Ada where you have like a concrete different type. Rust, the left side and the right side, even though they are called different things, they're specified at different lines of code and whatever, they're just the same type. Like Rust will not actually know that bar exists. It will just know that like there's a U32 here now. It's not a preprocessor, but it's just like, it will just transparently make this disappear. It's just a help for you to not write the code twice and be able to easily change like type definitions. So keep that in mind when I'm going into my examples that are following. Patterns. Another side, before we go into actual pattern types, patterns in Rust are similar to the whole case patterns that you have in Ada. You can match on something, and then like this is almost the same syntax. The Rust formatter just doesn't put spaces between the dots. Otherwise, like it's pretty much the same thing. And there's other syntaxes like the OR pattern where you just like do separate things. Like is this a cat, dog, or bat? And then you if it's one of these, then you go into .arm. When others, you go into the rest. And these kind of patterns are what we actually want to use for specifying subtypes in Rust, because we already have the concept of something matches some specific subsection of that type, and we just want to reuse that because we don't want to duplicate another system. So that's what we're basically trying. One cool thing about Rust, you can specify patterns that are matched together. So here I'm matching on 2 variables at the same time, and it's required that the first variable is in range 1 to 10, and the second variable is dog or cat. Then we go into this arm, and if it's 10 to 20 and dog or cat or bat, then we go into this arm. So you can combine multiple types and check them at the same time together, and that's something that we want to use in our pattern types too. This also works in Ada, but you need to specify more complex bounds there. It's not like a built-in thing directly. You need to do these runtime checks as far as I can tell. So how would this look? We had the earlier example of non-zero, and now my plan for the very far future is that the standard library will actually replace the non-zero U32 type with this type alias. Like it will literally be a U32 is 1 ... So a U32 that starts at 1 and can be any value after that. And similar thing for null pointers. We don't use the not keyword because we are Rust. We're using sigils and shorter stuff, so we use not, the bang, and then null. This syntax might completely change, depends on what the language team decides, but something like that will happen. And so we can define those types that are already built into the standard library. So what else can we do? First, I already mentioned that pattern types do not do strong typing, so you do not get separate types. If you do the same type definition twice, it will be exactly the same thing. If you say U32 is 1 ... something, another person defining in a completely different library, completely somewhere else, same thing, same type. And for the language nerds about you, pattern types are not actually doing subtyping. Pattern types only coerce between each other, like the compiler will insert conversions, but there will be no like actual type system subtyping where the types are actually like subtypes of each other, like what happens with lifetimes in Rust. Lifetimes do a lot of subtyping, but we're trying to keep it to lifetimes and not explode that more. That might change in the future, but for now we're trying that. So, how do you actually create a pattern type? Up to earlier this week, what you had to use was a transmute, like unsafe code to convert an integer to the actual subtype. And now what you can do is you can just specify literal, just like in Ada, you specify literal and assign it to your subtype. And the compiler will just check, is this literal actually in range for that subtype? And if it is, then it will just merge it. And if it's not, then it will actually emit an error. On the other hand, if you're converting a variable, so you declare the variable here and you convert that, you need to currently use transmute. There's no good conversion. In Ada, you literally just use the type and it will do a runtime check for you. But we're working on that. And what we want to do is, thanks for the previous presentation, I stole your stuff. Here's a grade type, which is 1 to 6, and a passing grade, which is 1 to 5, German passing grades anyway. And you have a variable of type grade, however you get that value. What you then want to do is you convert that grade with try from into a passing type, and then you get an option back, because either the conversion succeeds, then you get the thing in your option sum, or it doesn't succeed and you get a none. You don't actually get the value. If it doesn't succeed, you don't get a value. Important stuff. Good that Ada and Rust are getting this right in contrast to other languages. There's lots of more stuff that I want to do. These things don't work yet at all, but Rust patterns, I want to basically, if you can write a pattern in Rust in like a match, I want you to be able to write a pattern type for it. So having combinations of like a type where the U32 must be between 0 and 100 and the string must be limited to specific things, and this is in combination. You cannot go out of this. These belong together. And maybe even at some point have constraints where like 0 to 50 means cake and 50 to 100 means fruit or something like that, where you can make more complex combinations of that. I want to, if you can specify it in a pattern, I want you to be able to write it as a pattern type, and we have a good plan for getting there. So, I'm almost out of time, so let's go to a summary. Generic modules, completely to do, not happening anytime soon. Don't wait for it. Contracts are work in progress. They're happening pretty fast, and I think they are already supported in the Kani model checker, so we'll just get them basically for free as a static check. Pattern type, I'm working on them. If you want stuff, complain to me. I'll try to make stuff work. My next step is idiomatic conversion, so the try from that you saw earlier. And where we've caught up, we have safety certification, and we're sound by default, pretty much modulo some soundness bugs that we're fixing, but like that's a compiler bug, not an actual language bug. Thanks. Questions?
So the matching on, constricting to certain strings kind of scares me. Why can't we just have the, having it just generic types that implement the trait, and the trait, because the trait can be private in your library or whatever. Because whenever I see it can be these strings, it gives me major JavaScript vibes.
Okay, the question is, why can we actually match on strings and say this could be cake or a fruit or something, and why isn't there some better system? I think, yeah. I don't actually know. It's a hard topic to do something better. They're really you can do runtime checks similar to the Ada runtime checks, or you can do this OR listing. We don't really have a better concept. There's ideas for integrating regex into matches or something like that, but that's very far off, and I don't know if we're going to do that or anything at all. There might be better ways to do this. I don't really know about it. I'm happy to talk about ideas, but yeah, I don't know.
Considering that you feel that Rust has caught up in terms of safety certification, my question is, how in Rust do you prove the absence of runtime exceptions?
The question is, how do you prove in Rust the absence of runtime exceptions? Well, similar to how we have Spark and Ada, we have Kani and Rust. It is a work in progress, but it does actually do the same kind of checking, and it is actually being used for pretty much the same things. We have 1 minute, so one more question.
Subtypes, will I be able to, if I expect a subtype in a function like a reference, will I also be able, or if I, not the generic type, will I be able to pass in the subtype without any problems? Or because it sounds like that you get this kind of subtyping then.
Can you?
assume I've got a subtype, range 1 to 5, and I expect a U32. Will I be able to pass in the subtype?
Okay, the question is, if you have a subtype, can you use that anywhere where you can use the normal base type of that? And the answer is you can outside of generic context first, because there's implicit conversion from subtypes to the base type, because every subtype is a valid value of the base type. But if you're using in generic context, we're currently figuring that out, how to implement traits for subtypes and how to implement like implicit conversions there. We're not using actual subtyping, so we need to figure out something better. But it might be that the end result is we actually need full-on subtyping. We don't know yet. I have a couple more minutes. Cool. More questions? Over there.
In Ada, you can define two semantically identical types, but with different representations. How would I do this in Rust?
The question is, how do you specify two semantically equal, but with different representation, like two types with the same representation for the use in the language, but a different layout representation? And I don't actually think you can do that.
Can you use constant functions in contracts?
The question is, can you use constant functions in contracts? Right now you can just use any runtime code because they're just runtime checked. Contracts are work in progress, and we're figuring out the details there, but the simplest thing was to simply make them just runtime checks at the start and the end of the function right now, and we'll figure out the details as we go.
Syntax highlighting didn't highlight the Rust code inside the precondition and postcondition make code.
Yep. So the question is, why is the syntax highlighter not actually catching those preconditions and postconditions in the contracts? And the thing is, the contracts are attributes, and attributes don't actually support expressions in them, and there were some bunch of hacks going on there. Like basically the attribute is a proc macro that generates some super secret internal Rust representation language. And we don't actually know where this is going yet. It might actually end up just being surface language syntax that actually doesn't use attributes. But like this is work in progress, and the language team would like us to be more using weirder syntax to start with, so we don't prescribe what the language design is going to go and end up with, and not get people used to something that actually looks like they want to use it in the end.
Currently there's an optimization with maybe where it can use like one of the invalid values to...
Yes. So the question is, if you, for example, use a non-zero type inside an option, what you get is the same size as the non-zero type, because the option knows like, oh, there's a zero missing, I can just use that for my none value. And the pattern types, actually that's the first thing I implemented. Before I implemented anything else in pattern types, I implemented if you do like 0 to 100, all the other possible values of your integer are now for free for other enums to put their discriminants in. So you can actually nest like 50 options inside each other, and in the middle there's a 0 to 100, and that will just be the same size as the original value.
And you can do it like explicitly to select the value you want for the...
Well, the pattern type the question is, can you do explicitly say like which bits are supposed to be there and which not? And the answer is simply the range that you're specifying, that's the valid range, and everything else is invalid. And if you specify like multiple ranges, right now the limitation is it will just pick the biggest space of invalid values and use that for everything. It will not actually preserve all the invalid spaces.
That's about time.
Cool. Time. I'm going to be in the hallway for questions if people want to back me about stuff. Happy talked about Rust, talk about Ada and stuff. Grab me.
Now we have 5 minutes, so we can take the picture now if you don't mind. So all the speakers, if they could come to the stage. By the way, I don't. Okay, green. It's working. So I will be giving you instructions for the time of your talk with a 5-minute Q&A. So you can talk and you can as long as you follow the times. Okay. And the Q&A will start. Don't worry, I will give you this.
I've been, every time I come up with something that I need and I start writing it, my blog might as well just create a library of sources.
Hello? Hi. Hello, I'm César. I'm a newcomer in the Ada and Spark community and ecosystem, and I've been studying cryptography and cybersecurity, and so that's what inspired me to write a big integer library for cryptography in Spark. Yeah. So why do we need constant time cryptographic primitives like big integers? We need them to avoid some side channels in cryptography code, and I wanted to be able to provide some strong primitives for building stuff in Ada. So yeah. I wrote a big integer library in Spark with designs and algorithms that were inspired by Rust's crypto begin crate, and all the functions that I wrote are in constant time unless explicitly named as such. But yeah, it's still some experimental code, so I wouldn't advise to use it in some security-sensitive context. But what I've been talking about constant time since the beginning, but what does it actually mean in the context of big integers? A constant time algorithm is an algorithm that will not have dependencies in terms of resources on secret values and values that we want to remain private. So it will not leak data depending on branches, on memory accesses, or timing data, and all the operations that you can do on those structures are always take the same time and the same resources. So we have no branching on secret values. We have no memory accesses that depend on secret values to avoid leaks due to cache access latency and such things. And for instance, there's a famous vulnerability in some RSA code that would leak some information about the secret RSA exponent by doing binary exponentiation and taking more time during the 1 than during the 0. So yeah, it's sorry about the quality of the picture, but yeah. But in some constant time code like that, the code is usually less readable because we have to use different techniques and avoid certain patterns that we don't want to have in our code. It's usually a bit slower because we need to always take the maximum amount of time for an operation. And sadly also, it's always a fight against the compiler because some optimizing compilers might recognize some constant time algorithm, some constant time construct, and decide to replace it by a faster and variable time construct. So for instance, in the binary exponentiation classical example, we transform the branch depending on a bit of the exponent into a conditional select that is implemented using masking and bitwise arithmetic. And we must take care to transform our condition into a mask properly in order to avoid some compiler optimizations. And that's all well and good, but it also leads to code that is, yeah, as I said, less readable and harder to understand. And that's where I think Spark comes in, because we can then prove the primitives that we use to build our constant time algorithms in Spark with contracts. So Spark brings obviously the assurance that we have no runtime errors, that we have always determination of our algorithms and all that. It also proves, it can also be used to prove our bitwise operations, like the conditional select or the conditional swap. And even though we cannot prove that these are effectively running in constant time because of all the considerations about low-level hardware things and optimizations, we can prove that they effectively do what we want them to do, which is select the values and swap the values as we want. And in fact, all constant time code, in essence, if it's not written in pure assembly, it always relies on best effort implementations We have to obfuscate our intent from the compiler. We have to add optimization barriers, and yeah, the best we can do to actually ensure that our code is constant time is to audit the assembly output and measure the resources used by our code when it's running. And yeah. In the library, on top of having proofs for low-level and bitwise operations, I wanted to have some higher-level proofs, including a proof that I wrote for proving the addition of two big integers. For that, I was quite surprised by the amount of code that you need to prove simple things in Spark, but I think that's for most proofs in formal reasoning, that it takes always much more Spark code and Ghost code than it takes actual logic to prove what we want to prove. That proof is available on the GitHub repository, but it's not yet provable by the gnatproof alia package. So for now, it's in a separate branch, but yeah, it works. My main inspiration at first, because I was trying out Spark to write this library, was to try and write a small elliptic curve implementation, and so that's what I did in a small test where I used the test vectors of an elliptic curve to test my implementation. We can define operations on a prime field by instantiating a generic package by defining the prime you want either at compile time or at runtime, and then instantiating the package you want. And a first version of that library is available in the Alia index right now. And yeah, that's. Any questions there?
When you say that actually constant time code needs to be written in assembly, is that a truism of the area? Or, because I can imagine different compilers committing different assembly code, but also different CPUs interpreting differently, or having microcode to specialize and try to make something faster within the CPU.
Yeah, so how does constant time code really can be ensured to run in constant time even in assembly on different architectures and all that? It's kind of an open question, because yes, as I said in the slides, even a simple instruction like div can be running in variable time depending on the operands. There are no real solutions today, I think, to that problem, and it's mostly guessing and trying to do our best. But to actually prove that some stuff is running in constant time, you would need a really deep integration with the compiler, an architecture, a language, and all that, and it's kind of an open question. Yeah.
I think ultimately this would have to be solved by the compiler, right? Anything else is essentially just a hack where we hope that the compiler is doing the right thing, and I suppose maybe we could just look at the assembly instructions and expect that it's just one of those where we know that it's probably constant time. So some sort of white person or something, but as said in the end, this should be done by the compiler, and I think that would be the proper solution. Like a compiler flag, or I don't know, like in C, maybe in Pragma or something, so that you could say this section of code should use only constant time instructions.
Yeah, so the question is that the observation is that such a problem should be solved at the compiler level mostly, and with specialized annotations to say that such block is in constant time and all that. And I can just say that I agree completely, because yeah.
Have you looked into branchless code or maybe some loop unrolling in order to make sure that things are just the way you write them?
Well, yeah, that's such. Where is what I wanted to write? So that those constructs and all that is just manual branchless code. It's just transforming a condition into a mask and then performing the two operations and then just choosing the operation that we want. It's a manual implementation of just doing branchless code in fact. So yeah.
In your code select, the condition you have chosen something different than a Boolean. What is the reason?
So in the conselect primitive, I used a different type than a Boolean to express the condition. I chose to use in the conselect, I chose to use an opaque type called choice that is in itself a mask. So it's not 0 or 1, it's 0 or the maximum value of a U64. And the reason is to kind of obfuscate what I want to do to the compiler, and also to avoid doing some transformation all over the place. For instance, there are some operations that already give me a mask, and I just want to be able to reuse it. And so yeah, I just built another primitive to do that. Yeah.
Submissions that last summer, but there are a lot of implementations, most of the implementations need to be done sometime. So there's a lot of research there, and perhaps we can switch to something like in another language rather than and see whether we can use it. So I was wondering whether it could be performance critical and could be used in a performance critical domain.
The question is whether the code is usable in performance-critical environments, and I would say that since the code is proven by Spark to be without runtime errors and all that, it can be used without assertions and all that, so that kind of consideration is already good. And there's always the fact that we have to run operations in a maximum amount of time in that, but that's yeah. The library that I wrote is not optimized for performance. There are some operations that I don't implement in the best way, but in the simplest way sometimes. So yeah, it could be used maybe with some development, but. There's not a lot of time left, so maybe one more question.
Maybe an observation. I don't think there should be that much difference between variable and constant time code, because in cryptography at least, because if we have much entropy, like, then all these optimizations, like, oh, that's 0-bit, I don't need to do that multiplication. In like half the case, it won't be a 0-bit, and you will have to do the multiplication. Like, so I think there's not much lost in the average case. Maybe like half as possible at some point. What I wanted to ask you is, so I guess you're not implementing a Karatsuba multiplication. You have like.
Am I implementing a Karatsuba multiplication? No, not yet. It could be. I could do it, but I haven't. In the original Rust grade that I got heavily inspired from. There is an implementation that decides at compile time whether to use Karatsuba or classical multiplication, and I just copied the classical implementation of multiplication because
During the implementation, how often did you have to actually look at the disassembled output from the compiler?
During the implementation, did I have to look often at the assembly output? And I did look quite often at it because I wanted also to check whether my code was vectorized properly by the compiler and all that. So I looked for when building the primitives. I looked quite often at the assembly output, and so yeah, it's maybe not a necessity always, but yeah. So thank you.
That if the compiler could supply like a flag or a fragment to say this is custom time, so you didn't have to worry how to hide.
Okay, thank you. Should I restart, the reboot? Perhaps? Okay, good.
So let's start from the beginning then. So thank you very much. So this is about a form of multi-precision arithmetic. And the problem with multi-precision arithmetic is that it is more cost extensive. You have a cost overhead. So that's where the parallel computing comes in. So multiple double arithmetic allows you to work more precise, but you still work with floating point arithmetic. So we are looking into making numerical algorithms give them a more broader range. Now, to make it efficiently and parallel, I'm trying to vectorize the multiple double arithmetic, and I'm going to explain how you can do that. There are two types of parallel computation. So the first one is high level, very straightforward. The harder one is actually not really straightforward, and I will just give some hints to that. Okay, so I'm teaching also computational geometry this semester, so I got the definition of a robust algorithm. A robust algorithm actually performs in the same way if you start to tweak the inputs a little bit. So typically we work with 64-bit doubles, but we can extend it. So the idea to extend 64-bit float arithmetic using floating point arithmetic goes back to the late 60s, early 70s, when people at some point they were still forced to work with 32 bits, but they could actually figure out how to create more precision. So I was using the packages QDlib a lot, and there is also the Campari library. My goal is actually to go to GPU acceleration. So I'm presenting this on a gaming laptop, which is actually already quite as powerful as the graphics cards and the big servers that I was using 10, 12 years ago. So computers are actually too fast. For users it's not a problem, but if you are a software developer and you really want to exploit your computer, it's a big problem. Okay, what is a multiple double? It's simply a sequence of several doubles. So if you work with complex arithmetic, you have a real part and you have an imaginary part, two doubles. Well, double-double is actually very much the same. Now, if your result can be represented exactly in one double, like you want to compute the number 8 here, then your second double is going to give you the accuracy at which you compute it. So with double-double, you have about 32 decimal places. Then you double again. With quad-double, you have 64 decimal places again and again. So that's the good thing. So you can still do numerical analysis. So you kind of have an error estimate. If your result is can be exactly represented by 64 double. The drawback is that you're not going to notice all that much with double-double arithmetic. Actually, your problems are going to become compute-bound. So your processor is going to work a lot harder. But when you get to quad-double, actually, you may want to have, you may want to do some parallelism. And then, of course, you can double it up. So you see the average number of floating point operations that you will have to do an addition, a multiplication, and a division. So here is why I am doing this. I'm working with Taylor series. So you may remember Taylor series from calculus. So here is a very nice series. So the exponential starts with the leading coefficient 1, but then the coefficients actually, they go down very, very fast as a factorial. If you only need 8 terms, then double precision will do. But if you need more, so for example, if you need 32 terms in your Taylor series to represent the exponential correctly, so also having these tiny components, you actually will need quad-double arithmetic. And actually 32 is a good number if you think about the warp size in a GPU. So typically we would like to work with 64 or 128. Okay, so here is the idea. So what happens is that when you do an operation with a double-double, it's going to do the operation and then it's going to renormalize it again. So if you do a quad-double, it's going to also renormalize, make sure that all the doubles that represent your quad-double are actually going to be non-overlapping. So that is going to have a lot of tests, ifs, and things like that. The idea is if you vectorize, you actually would like to postpone the renormalization. So here is if you want to add a sequence, so you have 52 bits of precision in your fraction, you simply cut your 52 in half and you insert zeros. So these zeros are going to fill up. So you could also think about if you want to do exact integer arithmetic, you would split your 64-bit into 32 bits and you would add zeros in up front. And these numbers will actually fill up. Okay, so double-double arithmetic is also referred often to error-free operations. Okay, I want to do inner products. So I want to multiply matrices, for examples. The reference code is going to compute just a sequence of sums of products. So for products, if you multiply two, say 13 bits, you can have a 16-bit, 26-bit number. So that's why a double-double, which consists of a high double and a low double, it's going to be split into 8 parts. The 8 parts are all going to have 32 non-zero bits and going to be filled up with zeros. So it sounds very complicated. So what we're doing is that here with one inner product in double-double arithmetic is going to be replaced by 8 inner products, but the 8 inner products are going to happen in double precision arithmetic. So computers are very good at doing matrix-matrix multiplication with double precision arithmetic. Multiple double precision inner products are replaced by inner products in double arithmetic. So that's what I mean by vectorizing. So here is the setup. It's important this is still floating point, and the numbers can still float. You have to prevent this by kind of renormalizing intermediately. So sometimes people say with a 64-bit double you have 53 bits in precision because you had that normalized bit. Now when we split a double in 4 pieces, we also have to make sure that these exponents are actually 0, negative 13, negative 26, negative 39. Okay, so so here is then the computational result. And in some sense this is already a parallel computation because inside the computer there are pipelines happening. If you do a double precision floating point operation, there's going to be the denormalization, making sure that the exponents are the same, adding the fractions, and then again a storing. So by rewriting so that first big inner product as many inner products of doubles, we actually get a lot more speed up and a lot more gradual progression. So if you go from in the left column there, so the ordinary, what I call the ordinary normal double-double arithmetic, you have immediately a penalty hit of 13, and then if you go to quad-double, you have again 12 factor. But if you do it vectored, it goes way, way more gradual. And this was, by the way, done on a very recent computer with a recent chip compiled with a full optimization. Okay, now 2 levels of parallelism. So the big point is that going from, say, 12 milliseconds to 9 seconds, you're going to notice. So that's actually the whole big problem of using multiple precision arithmetic. things that start to take milliseconds suddenly become seconds. A second becomes minutes, and minutes become hours. So the 9 seconds, you can actually, if you do this in a very straightforward, so I had to do 1,000 in a product, I can actually reduce this with using all the cores in that CPU. I can reduce it from 293 to 300, going from quad double 4 times more. I like speed up, but we also like quality up. So in some sense, if you use all the cores in that computer, you actually can do the same computation 4 times more accurate within the same time. Okay, so that's the nice type of parallelism. Here is a reference. So this is what I call the work crew model. Every thread picks up an inner product and they work through a job queue. And the only thing you need to be careful about is that when you increment your job counter, so every thread has done, it asks for the next job, that they can only do this. They have to do this in a critical section. And this can be very nicely implemented. So I think this is classic Ada. Okay, now comes the hard part. With GPUs, you can actually do the multiple double arithmetic. That's fine. But then there are the tensor cores. So the computer that I mentioned, actually it has a high-end Ampere graphics card in this. And what this experiment shows is that these convolutions, they can actually be reformulated as matrix products. So this is what we call data staging. So we have to make sure that the data is all properly arranged in vectors, and that we have very carefully, we know where the beginning is and where the end, and where are we going to write. So GPU code is typically very short. You just smash some kernel on, but the preparation for the code takes a very long time. And actually what I've presented to you here is kind of a first step in making these tensor cores, making them useful for higher precision matrix multiplications. Thank you for your attention. I'm done.
Questions and answers? I have one. You said you were using a 96-core CPU.
Yes.
Then you mentioned that you had only 6 times speed up or something like that? Or?
Yeah, so, okay, thank you. So these speed ups are actually only done on 1 core. This is, okay, I'm sorry. So the question is, I'm using 96 cores, and how come these are the speed ups here? In this slide, I'm actually only using 1 core, and I'm using the 96 cores to reduce the 9 seconds over there. This is kind of here the highest time, and I want to reduce this. Comparing to the 318. So, I mean, that's about, with quad double, it's about 10 times slower. What I can do here is if I have 1,000 inner products to do, and they are distributed among the 96 cores in that computer, and that reduces the time to 318. To 293 milliseconds.
Thank you.
Yes.
I think on one slide you mentioned the semaphore as a synchronization primitive. Have you considered using something like atomic variables with carefully tuned barriers to minimize the impact on caches to avoid like moving memory back and forth?
Yeah, so the question is, I'm using semaphores here. Have I considered using atomic variables? And I think I do. So there are these types that I can use, yes. Yeah. Yes?
So if you're using multiple doubles, like I'm wondering, are the multiple exponents really useful? Or then, because you said they have to be non-overlapping, so they have to be in certain ranges.
Yes.
So are the exponents useful?
Yes, so the question is, are the exponents useful? So the exponents, so in some sense, so here is how you could see it. So that's also a drawback actually of multiple double arithmetic. You cannot go to, so you still remain 11 bits of in your exponent. So at some point you're going to have overflow or underflow. So you have to do still numerical analysis. Yes, so the question is if these exponents are useful. Here they are not if you are just normalizing, because they all stay fixed. Yes, and that's actually what you want. Yeah. So in some sense for your numbers, you're only going to use, so here I generated all constant numbers in a very nice range, but it's actually this exponent that is going to matter. And all the other numbers, they are going to somehow carefully need to be rebalanced. Yes?
There are some jobs which last so long and that impacts so much the temperature of the processor that we have to have those like the relay and make closes that it ranks the load balancing of the task.
So your question is about the load balancing?
Yeah, meaning when you are parallelizing a lot,
yes.
What's the impact over the temperature and the control by the hypervisor of how the processor is going to heat?
Yes, so the question is about the temperature and when the so I don't know, so that the machine starts to get a lot more noisy when I run it, and the fans are really starting to blow very hard. So that's how I see that it is working, or I hear that it is working. But yeah, I have no sensors. I mean, there could be sensors there, but I don't know how the temperature.
Had the case that the hypervisor made a pause at the calculus in order to reduce the temperature because the fan was not able to reach its max speed for the heating of the processor, and in order to protect the processor, it pressed pauses into the execution of the calculus. You never reached that?
No, I never reached that, no.
Okay.
Yeah. Okay, thank you.
Thank you.
So hello everyone, I'm Christian, even though I go in the internet as streaksu, and I wanted to talk today about my experience developing device libraries for Ironclad using Ada. The agenda for this talk is going to be short and concise. It's going to be what is Ironclad, why was Ada chosen for the kernel, the reasons why I chose it, and how I apply this on device drivers with examples. But most of all, what I wanted to do with this talk is give a counter-argument to the idea that has spread on the internet about Ironclad and projects like it, projects like libgfxinit, which is part of Coreboot, which are projects that take spaces that are usually occupied by projects made in C or C++. And people approach projects like this with the idea of, the projects are interesting, but sadly they are written in Ada. Ada must have been chosen because it was some kind of vanity project or just because the creator liked it. With this, I want to answer to this with the idea that no, Ironclad is interesting, especially because it uses Ada. And maybe, if I can convince you, maybe you guys should try it too for your next projects. So, first of all, I know that most people will be familiar with Ironclad already. I've done several talks about it, but I want to cover a bit my basis. Ironclad is a POSIX compatible, partially formally verified kernel. It's hard real-time capable. This means that it has strict scheduling guarantees, that it makes its best effort to accomplish. And it's almost 100% Ada and Spark code. I say almost 100% because as every operating system, it requires some assembly code. It has some C code as well for things like an AML interpreter, because that is an extreme workload, and all the libraries that do that for the space are written in C. And it's free as in freedom using the GPL v3 license. What makes Ironclad special? It's mostly three things. It's mandatory access control, the real-time guarantees that I mentioned, which are done without compromising general purpose computing, and the pragmatic formal verification using Spark. I won't talk much about the first 2 points because it's mostly an Ada talk. I didn't feel comfortable talking much about operating system internals when it's mostly about language stuff. But I do have other resources that I will talk about at the end if you guys want to check them out. Lastly, talking about the project, Ironclad is only a kernel. Those of you that work with Linux distributions must be familiar with this. Ironclad uses the same distribution method. Ironclad is only a kernel, and we need to mix it with GNU tools, Xorg, and libc to make a complete system. The main distribution Ironclad, not the only one, but the main and open source one is Gloar, which is the one that is running this presentation right now, which is a mix of Xorg, GNU, user space tools, and the mlibc, which is made by the Managan project. So why was Ada chosen for Ironclad? It's a mix of three things mostly. It's the formal verification of Spark, the fact that Ironclad has a quite interesting set of challenges with all the embedded development and having to mix formally verified and non-formally verified code that Ada approaches best, and the fact that the specifications and toolchains are fully open source. Before being an Ada developer, I was mostly a C developer, and it's just so nice to be able to have all the specifications just at the reach of your hands instead of having to pay hundreds of euros for a C specification. So going into why formal verification is so important for Ironclad, when I mentioned the three things that make Ironclad special, it's really not that true that the three things have the same weight. When we talk about formal verification is a foundation for everything else that we build on the kernel. Formal verification basically allows us to guarantee that we don't have runtime errors and check the conditions that we set up on the code. And with that, we can verify that actually mandatory access control does what we want, that the real-time guarantees are accomplished the way that we want. And it just gives us this full set of tools that we can use to accomplish this that wouldn't be possible without formal verification. And when it comes to other languages, really the competition is not that close in terms of formal verification. C, C++ family languages have robust standards, even though you have to pay for them, but it is what it is. And good open source toolchains, GCC, Clang, all the biggest tools are all C-centric. The problem though is that it has no language safety facilities, which makes formal verification of C extremely hard. And C formal verifiers are either obscure, non-existent, or you have to pay 20,000 euros a month to use them, which big problem. When it comes to Rust, the other big option that everyone just tells me, well, why did you not do Ironclad in Rust? It has a really good community and FOSS culture. It's a thing that I really wish that we had in Ada, a really good, strong FOSS culture. And it has a really good public image. When you mention Rust, people already think about safety. People already think about these things that they don't really think about as much when you mention Ada, just because it's not as much in the spotlight. The main problems with Rust, though, is the very bare bones standards. I say bare bones because ferrocene exists, but really it's not a Rust specification. It's basically a separate project that just verifies a set of toolchains for Rust with a concrete specification, but it really does not reflect on Rust. And the verifiers are very mature. In previous talks, we heard about Kami. It's a tool that I have tried personally. I was not happy with it. It really doesn't have much in terms of the features that Spark offers. I will also have to use Rust, and I will not develop on that point. Then it comes Ada. I know that we have all the logo with the coin. I just really like the bird. I'm sorry about that. It has really robust standards and really good open source tool chains. And Spark really is state-of-the-art when it comes to open source formal verification. The only problem that Ada has, though, is that it has a really thin community. And much of it is not centered on open source. I will not talk with you, I will not tell you all the stuff about how Spark works after 5 talks talking about it. But basically all the important stuff is that it has pre and post conditions, it has the whole control, check and flow, and for what I want to talk following this is that all of this has to be written. It's all a thing that you have to go out of your way to do. And it takes a lot of effort, especially when we talk about operating system code, where you have a mix of formally verified and non-formally verified code, hardware interaction. And all of this brings me to talk about how formal verification in terms of operating system code is extremely hard. Those of you that are into the field will also know about SEL4, which is a microkernel similar in scope of verification to what Ironclad wants to do. And they report that it takes around 20% years to verify 10,000 lines of C. For Ironclad, it's a bit better because we use Ada. It already puts us in a better position when it comes to formally verifying than C. But still, the scope is much better with Ironclad. Ironclad is a full POSIX kernel, implements all POSIX behavior. It's not a microkernel that only has to manage talk between servers. So we do have to pick our battles if we want to put Ironclad in a good state of formal verification before we got into retirement. Basically how we start is that we start from the things that are closer to userland. That would be process management, mandatory access control and security. And we work all the way back from higher to lower priority to the things that are closer to the hardware. That would be going from the scheduling logic to internal kernel access. Thankfully, Ada helps though with Spark mode off that lets us mix unverified Ada modules, unverified specifications, and mix and match them into being able to delegate a bit of the work for later and expose safe interfaces for unsafe code. But there is more to it than Spark. Hardware developers are, initially the set of slides where hardware developers are sadists. I was told that I should not be putting that on a FOSDEM presentation, so we just left it that silly. This is a part of AHCI, which is the protocol used for SATA and similar disk access. You will notice, and I don't know how well it will translate from afar, but has several fields that are like 3-4 bits in size. It's a whole mismatch of types, all in the name of saving space. But languages struggle a lot to represent this. See, for example, you have to use bit fields. Bit fields are a minefield, though, for issues regarding endianness, for issues regarding the clunkiness to use. This solution is not really ideal. Rust straight up has no way to represent this. This is a crate created by a user that represents this behavior, but again, this is not maintained by the Rust community. It has no way on the specification of Rust or Ferrocin to do this. And you still have problems of type safety, like you're reducing the use size, which is a 64-bit type, to 4 bits. It's just a mess in terms of type safety. In the meantime, though, Ada just handles it perfectly. You can define your own types with your own bit lengths. You can compose them using record representations, and it just handles all of this flawlessly without the pain that the other languages have. With that as well, we come to Ada runtimes, which I think is the biggest reason as to why Ada adapts better to operating system work when compared with other languages. When we think about language runtimes, most of them we think about monolithic blocks where we cannot negotiate anything with the language. When it comes to Ada, though, we have the whole set of restrictions that lets us pick and choose what we want the runtime to be able to do and implement. So if you want an use the runtime in a stage where you don't have memory allocation yet, you can just disable that for the time being, or disable the whole floating point subsystem for the whole kernel, as we do for performance reasons. And truly, this is one of the best things when it comes to adaptation of Ada into weird conditions, weird runtimes. With that, I wanted to come to the presentation. If you guys want to follow progress of the project, check the source code, download your own distribution for testing. You can go to ironclad.nognu.org. And I would like to thank these organizations, the Free Software Foundation, Ada Core, and the Limine bootloader, which is a bootloader that Gloire uses, along with the NLNet Foundation for giving us funding and resources to continue the project. And I would also like to, thank these people as well. Yeah.
And then the Q&A can start. You still have a couple more minutes if you would like to go into any details.
Oh yeah. Well, I guess that I could also do a little showcase of the operating system. So all of this is Gloire itself. It features terminals, file managers. It just was there. Pretty unlucky that as soon as Serenity crashes. Well, it's fine. Yeah, any questions? While you do a question, I will just reboot it real quick. Go ahead.
Do you know how many people are using your operating system?
So we know of people. The question was whether we know how many people are using the operating system. We are aware of distributions that are made by other people for their own uses, some of them internal testing at companies. So there are some hobbyist users as well that use the operating system, but we don't have really hard numbers. We don't have any kind of telemetry that lets us know about that. Any other questions?
What is the source of time? Did you select a special hardware for the source of time?
So the question was whether we selected any specific hardware for the I didn't hear well the last part. Was it for the implementation of the operating system or for the...
No, for the source of time in other use.
Oh, for the source of time. For the source of time, okay. So depends on the architecture. Ironclad supports two architectures, x86 and RISC-V. For x86 we use the HPET as well as the LAPIC interrupt timer. The HPET for high precision timekeeping for things like counter calibration, and the LAPIC we use it for day-to-day tasks like checking intervals. And for RISC-V the port is not far enough yet to what I can give a comfortable answer. Any other questions? Well,
you still have 3 more minutes if you would like to go with the...
I will try this. I will definitely try. It's actually really, I was joking with another project. Where is it? Reset, perfectly fine. Just gonna take a bit. Okay, there we go. So this is Gloa. Shame that the introduction had to be, to the actual features had to be with the display manager crashing, but this is it. It's running XOR, has its own file managers. That would be the files for the slides that I used. It also has its own applications that are ported from other Linux distributions like calculators, screen shooters, features, also a few games that I will run GLX gears by popular demand. Those they are. Also features Solitaire as well, along with other games. Has again terminal emulators where you can do the typical Linux ritual of doing a neofetch. And that's it. It's just a fully featured general purpose operating system. Yeah. Wow, that's extremely unlucky. Yeah, it did. You're right. It's fine. I think I embarrassed myself enough.
It's fine. It's better software.
It's better software, yeah. Well, anyways, yeah.
Thank you very much.
Lo he probado.
Hello, welcome. This is AdaBots, the award-winning system for connecting a bot inside a voxel world with a real integrated development environment. And we use this for teaching. I use this in my household for teaching our children, but it's also excellent for teaching adults. Anyone who wants to learn Ada, I can of course highly recommend it. So what is AdaBots? It is programmable bots in a voxel world. Originally it was using Minecraft, but then I switched to using minetest, which is now rebranded to Luanti because it's open source. Programming with AdaBots is visual 3D problem solving. You encounter something in that world with your children, with your students, and then you try to think about programmatic solutions to that. Like you get stuck in somewhere down deep where you can't get out, you can get your bot to build a staircase up and walk out. Maybe your child wants to build a house, you can do that. Anything you can imagine, you can use as a programming challenge for your children. It's also real software development, as in you connect these bots to a real IDE running a debugger with Git version control. It's not like visual drag and drop things, it's real code. So my teaching goals here is, first of all, I want to do this because I got frustrated with, there's so many systems out there for teaching children how to code that actually teach you a very specific, domain-specific language, and you then have to translate your skills into real programming once you want to do that. What I also have found frustrating about other systems is that they were often this walled garden where you kind of had to trust someone on their word that they're not going to, kind of rug pull or increase the price on a closed source project. So I wanted from the beginning to build all this up as open source components so that the community can help, and so that you can rest assured that the system will still be working the same way 5 years down the line, 10 years down the line. Freedom is important to me, also inside of AdaBots. So inside Luanti, you have your own private server. You can walk around and do anything you like to do. I also really wanted to make an environment that I could feel comfortable with my children interacting with. So I didn't want something with the glorified violence. I didn't want the focus to immediately be on you're going to be making a game. I wanted to have more freedom to allow the child to learn a real programming language and then start applying it to real problems. I also, as a parent who homeschools, I also realize it's really important to have a system that you just open it up, you just go to the website, and you don't have to do all of the setup yourself as a user. So it's a plug-and-play system, thanks to having a code editor that works inside your browser, and also a Luanti client that works inside your browser. Okay, that's the introduction, what AdaBots is. I'm going to go into a little bit of background. Where did I come from? How did I come to these ideas? And then I'm going to show you a demo. And then I'm going to talk more about the principles and, of course, why I chose Ada as the programming language for this. And finally, a roadmap of things to come. This is me when I was 8. I was coding, well, I wasn't coding here. That came later. But I loved that powerful feeling of entering a command into a DOS terminal and just seeing it instantly executed. This wouldn't have been possible if it wasn't for my father knowing what these commands meant. And later on, when we got Linux, and it came on a CD, it was great. And my mother showed me more of that. So I was very privileged to have two parents with a lot of technical background. Years later, fast forward to I'm a teenager, and my brother and I were really doing our best to waste our afternoon. We had a Minecraft server, and we loaded this mod called Computercraft on it. And it makes these bots inside the world, and they can move around, and they can place blocks, and they can mine. And before long, we weren't doing anything by hand anymore. Because, you know, why go through all that arduous process of going down into the mines and mining things and placing blocks when you could just write one program and then go to sleep, log off in an hour, or the next morning you come back and the whole structure is built. So here we have a maze built here. And if you were at FOSDEM 2 years ago, you might have seen some of these mazes because then we had a stand and we challenged people. A lot of children came through as well and were challenged to get their bot outside of the maze. You could win a little prize for that. But one thing I really didn't like about Computercraft and still don't like about Computercraft is the interface to programming. So this is how I was programming these bots. You have just this text, Lua code, which it does duck typing, so it's not strict at all. It doesn't check anything for you. You just have to make sure that you know what you're doing, and you have to scroll around in this little window inside the game of Minecraft. And I thought, well, how can I improve that? You know, it was really difficult being a Minecraft mod where you had to edit jar files in there, and this is already very good for what it is. But a few years later, I was at Ada Europe, and I was able to participate in a remote I/O tutorial by Philip Muntz. And this is a great software project that solves a kind of similar problem, or at least I realized I could apply his solution to my domain. His problem was he does a lot of embedded programming, and you have this chip that you want to run your program on. But first of all, you have to cross-compile and then upload to the board. And then if you want to debug, you actually have to connect two little wires to the JTAG, and it's really complicated to do that. So what Philip thought of, and what I'm calling fetch, evaluate, execute loop, kind of like a REPL. It's like a REPL, but it's two different systems. So you have on the board, you have just this super simple little program that's just asking for an instruction and then executing it, and then sending back over in this case, over USB and paint line onto the computer. And then on the computer, you can have your whole dev environment, including a debugger, and you don't need to build anything for specifically debugging on the chip. So yeah, check out libsimple.io if you want to do I/O programming in Ada, because it makes it a lot easier. You can also take the same program and just compile it with a different implementation backend and upload the same program to the board itself. So that so for development you have a quick cycle where you can just edit and run, but then you can use the same code to deploy. So I realized that I could do exactly the same in Luanti. I also realized I weaned my dependence on Microsoft products a little bit by moving to an open source, lightweight C++ clone of Minecraft. I'm not getting any dirty looks. Oh, maybe one. There's a Luanti developer in here, and they are not a Minecraft clone. They're a voxel engine. But the neat thing is, it's so lightweight, I'm able to actually compile it for the web. And so if you go to adabots.net, you don't have to do any of the setup, because automatically in the background a Docker image spins up with your minetest server in it. And in your browser you can have a minetest client. Sorry for saying minetest so much, it's Luanti. It just changed its name this year. So anyway, so this is the architecture. We have a server running, and that contains bots, and those are doing this little fetch, evaluate, execute loop. And then you have a client that connects to that to look around in the world. And on adabots.net you can have one for each child as you like. And then you have your code editor running on your own machine that compiles a program that runs on your own machine, which sends these instructions to the bot. Anyway, what it makes for because the children don't understand all of this architecture behind it, of course, but what they understand is that here's a fun, entertaining world where they can all log in and they can see what they're doing, and each one can be doing their own tasks. And so here's a bot next to a tree that has just been cut down. And that's a simple, check if there's wood in front. If so, mine it and go forward, and then start a loop going up as long as you can mine a block above you, then mine it and go up so that you take out the whole tree. And yeah, I'll show an actual demo. That's better than just explaining it. So if you sign up on adabots.net, give me some of your money. It's an open source project, okay? But what we do is software as a service, really. We set it all up for you. If you sign up on adabots.net, you get in the middle here you can add as many students as you like, and you get two buttons, one to open the minetest world, and that opens in your browser, and the other one for VS Code Web, which also opens in your browser, and they're connected to each other. So here's an empty program shell here, and we're going to run through a non-trivial program without pressing any of the buttons, which is just for introducing the child to what the bot can do. You can just press the buttons. So that in that way I can start already when they're 5 years old, just understanding the concepts of what we're going to do. But of course you need to wait until they can read and write and type before you do this. So let's build a bridge. That one doesn't work, but okay. This is the bridge we're going to be building. First we're going to place a block, we're going to go up and then forward. And we're going to do that in a loop, and you can see that that will make a staircase if we put that in a loop. But we only want to do it 3 times, because if you just do loop, that would be infinite. So we put in 4i in 1.3. Then we're going to build the flat part of the bridge, like this. Again, a loop, just 2 instructions in there. And when we get to the end, we're going to go down and note that we'd go for 1 to 2, because otherwise the floor is already made there. This entire thing, we're just going to give it a name. We're going to put it in a procedure called pass. That's 1 pass over the bridge. And then what we're going to do is we'll line up for a second pass next to it. So we'll go forward, we'll go down, we'll turn left, we'll go forward, we'll turn left, and now we're set up to do another pass. I'll skip over that. So now we've done a second pass, we're going to line up and we're going to make some barriers on the side so that you can't fall off the side so easily. And again, we're going to okay, you can kind of see it moved around. It's just shifted over to the left and up 1. Okay, and if you do another pass on top, then we've got our barrier. And all the time when you're doing this, you can just comment the code that you've already run, and you can press some buttons with your child as you write the things in the code to explain what you're adding. But at the end of it, you have a program that does the entire it does the entire bridge in one go. So you can I'll quickly go through why we chose Ada. It's a very type-safe language. It's high level. It's it's tried and tested. I have a vehicle from 81, and it still runs. That means it was built right, and it's the same with Ada. The latest standard is from 2022, but there's so much materials around, and it's got so many of the basic principles right from the start. Like being case insensitive, it's a no-brainer. Having words for everything instead of curly braces, that helps a lot in teaching, because the case insensitivity, every child, when they first write their program, they write it not caring about the casing every time, and it just works in Ada. I've already talked about this, so I'm just quickly going over it, but I'll just say that children don't like to be coddled. They want to really be a software developer, so we let them do that.
So we made this safe environment for your children where you can learn. It's plug and play. And we have a lot coming. So I'm just going to open it up to questions since we only have a few minutes left. Yes?
So you mentioned that this real. So basically, the way I understood that is that the code runs outside of the minetest server, and it interacts probably with like a Lua mod, very simple, that just receives commands. Can the bot detect or like perceive its environment? Because I've worked on like bots that run inside of the client, so it's kind of for like cheating on servers that allow it. So basically, they are able to like look at what's around them and then react to that.
Yeah.
I think that would probably be like beneficial for this project. One thing that I'm wondering about is if you think that if they can interact or if they can perceive the environment, do you think that this sort of like remote model will be performant enough to allow for like complex bots? Because one thing that I've noticed, even just like between like C++ and Lua, crossing that boundary for every block that you want.
Let me just repeat your first question first. Can the bots perceive the world? Yes, they can. They can look in the same spots as they can dig and they can place.
Okay, so it's very limited.
Yeah, right now it is. It's actually on the roadmap to, right there, third point, is to actually see players and see a long way away. And I have an idea in mind of an expanding cone of nodes that it is able to see. So it can look through air and water, but not anything else, and then it just returns a list of all the objects. Your user program does get very complicated very fast, but of course, I mean, we envision this also being used for adult students, universities, in high schools. I'll also give you here a promo code if you're one of the 200 first people to sign up. This one isn't on the online version of the slides, but it's FOSDEM 25. It gives you 25% off your first year. And also, yeah, I'll just say this because the video isn't loading, but my children had a great idea after we built a spiral staircase, and they kept falling off in the middle of the staircase. I said, let's build blocks there. And they had already seen how complicated it gets when you build, because you have to walk backwards as you build above one in front in order to not run into your own blocks, right? So they said, how about we just have 4 blocks simultaneously dropping sand below them? And that's perfectly possible, and that's in the video here. There's 4 bots next to each other. So your program can address multiple bots simultaneously using tasking in Ada. Any other questions? Thank you.
Then this settles the Ada DevRoom. This was the last talk of the day. I would like to remind you that you have stickers not only from Ada but also for AdaBots. So if you would like to grab a card for AdaBots to remember it, you are more than welcome to do so. Thank you very much for everything. If you have any feedback, please come to me now and tell me what could be improved or what could be changed. And I will be more than glad to take your feedback. So thank you very much. And also, if you are interested in becoming part of the Ada community, like officially, and you may be a professional, or you may want to communicate with the rest of the community in a more professional manner, we have the European network, the Ada Europe. There is a Belgian one, a Spanish one, Ada Spain, Ada France, and in the coming months also the Ada User Society for a worldwide, more professional or informal, also to network if you would like to use. So thank you very much.
Тест, тест, 1, 2, 3, една патка пресича, две патки пресичат, всичко е наред.
Добре, няма хрум аудио, така? Имат. Чакай, я го змютни. Тест, 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 тест.